So I am a residential electrician by trade. I went to school, got a 2-year degree in it, and I actually love electrical and everything about it. So let's get started. And my name is Dirk, and this is how to perform your residential electrical inspection course. So this is not a code course, although we are going to be referencing the NEC, the IC, or the IRC. These references is good to know, especially in your back pocket when you're doing these inspections. So, but always check the course out, check out the check out the codes so that you're familiar with what's going on. But also remember that any jurisdiction can oversee whatever the code says. So code is not law, but it is code to be followed because it's a safety thing. So this course is designed to help the student understand some, but not all of the electrical installation. And we're going to run through it pretty fast. Even though this is 3 hours, this is going to be pretty in-depth. So remember, local codes and building standards may have exemptions. So just remember that when you're doing your inspection. The primary responsibility of a home inspector when inspecting electrical systems and components during the home inspection is safety. Safety of the instructor and safety of the client and safety of the building occupants. Sometimes when I go through homes and I find something that's very unsafe, I make sure that I put a note on the counter for the occupants that are in the house. This is also one of those few areas that most home inspectors would report in need of correction and then go into build the code or update or whatever it is. So the absence of GFCI protections in the kitchens, for example, things like that. We want to make sure that we're regarding when the home was built too. So GFCIs might not have been present during that time, but we do want to make sure that they are updated for safety reasons. The home inspector should be understanding the codes and evaluating these panel boards, understanding the electrical systems, the distribution, all that fun stuff. So according to the InterNACHI Home Inspection Standards of Practice, the SOP, a home inspector is not required to do anything that the inspector thinks is unsafe, including removing the dead front from electrical cabinets or panel boards and exposing any electrified items, anything that's live or hot. Stay safe during the inspection. Do not endanger yourselves or other people around you whatsoever. Use personal protective equipment or PPE. Take the InterNACHI free online safe practices for home inspectors at www.nachi.org/safety/course. Be sure to refer to the SOP and read the requirements and all the exclusions for conducting these courses. According to the InterNACHI Home Inspector Standards of Practice, the inspector does have jurisdiction when it comes to, yeah, you have to look at my wires. No, you don't. You don't have to go in here if you don't feel like it's safe. Okay, do what's safe. We all want everybody come home safe. That's the whole reason why we work, is so that we can spend the money. You can't spend the money if you're dead. So a home inspector is not required to remove that dead front cover. I want to say that multiple times through this whole entire course because I want you to understand that. From any electrical panel board, cabinet, enclosure, or box. The image here above is a dead front cover. There is a cover that goes on this right here. I just took it off. This is not live, so I can touch it. Just kidding. But it's for demonstration purposes only. Okay. We are not recommended that you put stuff in there and things like that. Because if you're in doubt about something, make sure that you say that you want this further evaluated by a licensed electrical contractor. Okay. We definitely don't want to poke or do anything that makes it unsafe. Safety is the key in home inspection. That's what we are. We are safety inspectors. We are not code inspectors. Okay, one of the challenges of facing home inspections, doing the electrical portion of home inspection, is getting the terminology right. A lot of people don't get this right. So many home inspectors end up looking inexperienced. They look unprofessional. That's why I got the tie on today. So by not knowing the correct verbiage, you can actually make yourself really sound bad, and then home inspectors actually get a bad rap from it too. So here's a list of common terminology that we use in the electrical systems. Now, read through these lists, take a screenshot, do what you got to do here because you're going to refer back to these a lot of times, and some of them have multiple meanings too. So, amplicity, that's the maximum current that conductors can carry without exceeding the maximum temperature rating. So, appliance, that is the utilization of equipment performing in functions such as clothes, washer, dryers, things like that. Okay, AFC is arc fault circuit interrupters. That's going to sense if there is some sort of arcing going on, it's going to shut off the power. AWG, that's another thing that we will say quite often. It's the American wire gauge. It was established in 1857, believe it or not, and it's not changing. So we're going to keep that going, and that's how thick the wire is. The lower the number, the thicker the gauge. Okay. AWG tables are for single, solid, and round conductors. The AGA standards wire is determined by that cross section area of the equivalent solid conductor. So when you're looking at the wires, because there are also small gaps between those strands, a stranded wire will always have a slightly larger overall diameter than a solid wire of the same AG quality. So, anyways, bonded, we're gonna be talking about that and how it's connected. I did a couple of videos on electrical already, so I really love electrical. Go back and check those out if you can. It's Electricity 101 and 101 Part 2, bonding and grounding. So those two will really help you understand bonding and grounding because a lot of people don't understand that. Branch circuit, that's something that we're going to be talking about. It's how conductors, wires basically, run between final overcurrent protection devices in the panel board and the outlet, such as like your lighting fixtures, your receptacles, things like that. It is a conductor between the final overcurrent device protecting the circuit and the outlet. Uh, so the branch circuit wiring enters the panel board cabinet through cable clamps installed in those knockouts. Several kinds of clamps are available, including those metal ones. They got plastic ones. They got lock nuts. They got tons of different clamps that can be used now. It's really good to understand how they work. So it's good to walk through like at Home Depot or Lowe's or in some areas, Menards, and just check out some of that stuff too, just to get yourself familiar with it. The cabinet is a mounted enclosure with a swinging door. So if I had the face on this, it would be that door that opens up. Okay. Um, Current, a measure of the rate flow of electricity through the conductors. Current is measured in amps, and we're going to talk about that. The dead front cover, I also like to call that your blast shield because if you're taking off that cabinet, you want to kind of hold that up just in case something does explode out of there. You don't want something running out at you either. I've had a rat run out at me once. The dead front of the panel board cabinet protects the person from the live parts within that panel board. A dead front is without live parts and exposed to someone without operating size of the equipment. So according to the InterNACHI standards of practice, you are not required to remove that. So several times I'm going to say that. Device, a unit of electrical system, such as a conductor, that is intended to carry or control but not utilize the electricity. The disconnection means, okay, this is a device that the conductors of the circuit can be disconnected from their source or supply. The feeder is the wires that are bringing into the sub panel or the panel. So that would be coming down here, attaching to here, here, and here, and your ground would be over here. That's kind of what that's talking about. Your GFCIs, those are the little buttons that you see, or they actually have them in circuit breakers now too that have the test buttons. So there's a couple different ways you can see the GFCIs. They stand for ground fault circuit interrupters, or a lot of people just call them GFIs, which is fine. Either one is fine. Hot wire, that's not the ones that go in the fire and you take it out and oh, it's hot. It actually is the current that's carrying through the wire. So if you touch it, it feels like something's going to sting you. So that's why they call it the hot wire. The hot wires are the black wires, sometimes red, and yeah, that's about it on that. A line that refers a line that refers to the line that's actually going into the equipment, into the power equipment and the terminal or whatever it is. Okay. A load that refers to the outgoing power. Okay. So you got your line in and then you got your load that goes over. Your main breaker is what disconnects the entire electricity from the house. Normally now these main breakers are on the outside of the house, not on the inside anymore, because if there was a fire department can quickly shut it off. Okay. A meter, that's where you actually get the cost of electricity from. Those big meter base is what that attaches to. So it mounts so that you can get charged electricity. It is illegal to tamper with that. So just FYI. And then we got the neutral wire. Okay, so looking at the neutral wire, the ground conductor of the service, the feeder, the branch, the circuits, this is commonly called the neutral wire. Um, and it is required to be either gray or white. Neutral is sorry about that. That's something that's going on my screen here that's stupid. Sorry. The ground service conductor is what we call the neutral current carrying conductor. Many inspectors refer to all grounding conductors, the white wires in the picture there. Okay. In all branch circuits as neutral conductors or neutrals because they are all connected to the ground neutral conductor in the service. So all the service panel. So if this is connected here, all my grounds would be here and my neutrals would be here. Because of this bar, they're actually connected together, and that's what that means. But if I disconnect it, the ground should be separate, and this would tell me that it's actually a sub panel, not a main panel. So that's kind of how that works. Okay. Uh, the outlet. Now, an outlet is a point of wiring system where the current is taken to the supply equipment. Examples of outlets are like your receptacles, your light fixtures, your smoke detectors, those appliances. A switch would not be an outlet, okay, because no current is taken at the switch. Current supply passes through the switch as you turn it on and off. Okay, overcurrent protection devices. An overcurrent protection device is set up to open the circuit when the circuit exceeds that set value. Overcurrent protection devices are usually circuit breakers and fuses. Other systems include your relays, those are found on motors, the poly switches, which are resettable fuses. You see those on those strips where you plug in a bunch of power strips, and then they have that one button on the side. That is your poly switch there. And then you also see them on GFCIs and AFCIs. The panel board contains bus bars. That's what these are here. Okay. Terminals, overcurrent protection devices, and mounting hardware designed to be enclosed in the cabinet or box. In residential wiring, the panel board is usually not distinguished as a separate piece of the equipment from its cabinet because it's normally installed inside the cabinet enclosure at the factory. A receptacle. A receptacle is a contact device installed at the outlet for the connection of an attached plug. So a receptacle outlet, an outlet where one or more receptacles are installed. Now we're going to talk about something that I call a lot is Romax. And Romax is a trade name. It's a non-metallic cable. It is most common in most homes across the whole US here. The proper name of the cable is non-metallic sheathing cable, but I always call it Romax. A lot of people in the field call it Romax, even if it isn't. A 14.2 with ground would be contained in there, or a 314 gauge conductors, one black insulated conductor, the hot, the white insulated conductor, the neutral, and the bare wire, which would be somewhat. Let's see if I got one here. I can't even do it. So it'd be something like that if you can see that. That's what that looks like. And that's a 14 gauge. The SE and SC, or sorry, the SE or the service, the conductors, that equipment for delivering energy from the service utility to the wiring system of the home. Electrical service is the general term used to refer to all electrical service conductors and equipment. The service begins at the load end of the service drop or the lateral and ends into the panel board cabinet that houses the main disconnect, which would be this guy right there. Okay. The SE and SEU cables are, you can see it right in that diagram right there. Cables that are used for service, uh, service entrance is what it stands for. And I forgot what the R stands for. Sorry, guys. It's been a long day. And SEU, which is underground. And then the two common types are the SE cables. The images below show a SEU service entrance cable. The SE and the SEU service entrance cable is primarily used to convey power from the service drop to the meter base, and then to the distribution panel board, then to the main disconnect is installed at the main power board. Okay. SEU is the service or unarmed service electrical three-wire cable and two conductors and a neutral, typically used as an oval shape because the stranded neutral conductor wraps around the cable to create an oval shape. The SEU cable has a neutral conductor but does not have a grounding conductor. Since the neutral conductors and grounding conductors are connected at the point of service disconnect, the SEU cables can only be used up to the service disconnect to avoid significant safety concerns. Now the SER, reinforced, that's what it is. Service entry reinforced binder tape to reinforce its shape. It is round service electrical four-wire cable that typically has up to four conductors and a bare neutral. The cable is designed to be used in a feeder panel and branch circuit. CER or SER cables are equipped with a neutral and a grounding conductor, which makes them perfect for use after the service conductor. I know that was a mouthful. I totally get it. The basic terminologies that we use is, like I said before, the AWG. So like a number 4 AWG would be abbreviated into like 4, just the number 4, or it would be 4 AWG or 4GA. Once you get larger, the number goes down. So 4 is not as big as 3, and 3 is not as big as 2, and so on and so forth. Okay. But 3 would be actually pronounced 3-aught. So it does get a little confusing. But if you look on the wire itself, if you're looking at something like this, it would say 3. This isn't a 3, but it would say 3, or it would have 000 printed on it. So that's how you can kind of tell the difference. And you'll get it after a while. So there's common wires used in electrical distribution in homes and can be identified by a wire sized following by the number of wires in the cable assembly. So for instance, like a 14-2 would be two solid 14 gauge wires. Now, if there was a grounding conductor on there, it would be a 14-2 with ground, okay? Or if it was 12 with ground. And that's how they actually put it exactly like that. And you can read it right on the sheathing of it. So like this 14 gauge wire, I can't read it without my glasses, but it does say it on there. That's 14 with 14-2 with ground. Okay. So the pronunciation, the basic terms, we're still on this, okay? And then, like I said before, the number 0 refers to one, one aught wire. Two zeros would be a 2-aught, and 3 zeros would be a 3-aught. Getting the terminology right makes you sound more professional. But like I tell people when I mentor them is, try not to sound too logistical when it comes to this stuff. Try to keep it in layman's terms for your customer. But when you're talking to professionals, try to make sure that you're uh, sound professional. Okay, I like to describe electrical current in the motion of electrons flowing into a conductor a lot like water flowing from a pipe. And so the same fundamental principles really apply in that same way. It's not exact, but it gives us a good idea because we can't see electrons. So the same fundamental principles are like this. The bigger the pipe, the more flow it can handle, right? The bigger the flow it can handle. So smaller pipe can handle smaller supplies, right? This is the principle behind resistance. An analogy to understand electricity is the water pipe. When the voltage in the water pressure, the current and the flow rate, and the resistance in the size of the pipe. Get it? So current, flow rate, or amps, is equal to the voltage, the water pressure, or volts, divided by the resistance, size of the pipe, or ohms. Okay, so that's kind of that's how I describe it. That's the way I've been taught. Like I said, it's not exactly true, but it is pretty good on a good visualization. So let's see how this relationship applies in the plumbing system. Assume you have a pressurized water coming out of a garden hose. When you increase the pressure, more water comes out of the hose. Similarly, in the electrical system, when you increase the voltage, the pressure, the volts, or E is what they say, the current, the flow rate, the amps, or I, as it increases. Now, assume you increase the diameter size of the garden hose. More water will come out of the hose. Similarly, you will decrease the resistance in the bigger um, pipe, basically, or the bigger conductor that you have. So that's kind of how that works. So how do we do the Ohm's law? And Ohm's law can really help you. And there's basic functions of mathematical models that you can use to actually help you with this if you really want to. A lot of times we don't use this too much in electrical, sorry, in home inspections, but in electrical we use it quite a bit. Uh, so we want to make sure things are safe for the customer. So this allows us to understand why, for example. So a 30 amp fuse should not be connected to a 14 gauge wire. Why? Because the resistance is going to be too much and it's going to burn up that wire. So same thing's true when you're using your electrical cords, especially those orange ones, and you want a light or something that's plugged in, or maybe you're running a motor or like a compressor or something like that, that that cord will blow up or burn up. So Ohm's law defines the relationship between the voltage, current, and resistance, and I is the current. Okay, that's what it means. Uh, Measured in amps, which is A, and R is the resistance measured in ohms. So, and then it has a Greek symbol, I believe, of God for that. And E is the electrical potential, the voltage. And watt is the power measured in watts. So I always think of watts as the light bulb. The higher the watt in the light bulb, the brighter it is. Amps measure current. The volume of the current, the number of electrons flowing past any given point per second, is measured in amps or amperage. Okay, volts measures pressure. The pressure under which the electricity moves is measured in volts. Electricity arrives at the household current at a pressure of 120 or 240 volts. Now, watts is measured power. Power is measured in watts, and you can compute wattage by multiplying amperage and volts together. Hope that made sense. As we saw with Ohm's law, resistance is a key to a conductor's ability to safely deliver that amount of power that the circuit needs. Think back to that pipe. The bigger the pipe, the lower the resistance. Okay, so uh, when you're evaluating an electrical supply, we need to recognize the copper and aluminum conductors are not the same. Although they are both commonly used in residential supply, copper inherently has less resistance to flow of electrons than aluminum does. So for that reason, aluminum conductors are always one size or two bigger or larger than the equivalent copper one. for any given amperage. For a commonly installed 200 amp service, the service entrance cable, the SEU, between the base and the main electrical service panel with the integrated main disconnect, of course, will have a number 4 or 4-aught aluminum conductor, or the hot, which is the 2 aluminum wire. Remember, the lower the number, the higher the bigger the volume it is. So looking at the table, we can see that the 12 gauge wire is, I'm going to point at it, but I'm not pointing at the same thing, sorry. The 12 gauge wire, the copper, is the size for a 20 amp breaker. The wire gauge is permitted to be bigger than 12 gauge when connected to a 20 amp or 20 amp breaker. So a 10 gauge wire is used instead. So the 10 for a 30 amp and so on and so forth. So you want to make sure that you're looking at both of those when you're doing electrical inspections. When you're taking that off, you're looking at the numbers, making sure that things look good. When I first started into electrical, somebody gave me the good idea is to go to one of these home improvement stores and actually get some clippings of the different sizes, so that way you have them in your pouches and you can do that, or you can buy the gauge too that will tell you. So it's a couple good things to do. All ungrounded branch circuit and feeder conductors must be protected by an overcurrent device. The overcurrent devices consist of circuit breakers or fuses. They are installed at the beginning point of the circuit where the conductors receive the electrical supply. The breaker prevents conductors from carrying too much current or above that determined allowability of that amplicity. The breaker will automatically open up the circuit and protect the conductors if the current is too high, and it may create a very high temperature hazard. So we don't want that to happen. So that's why these circuit breakers will turn off when they have that. For small conductors, commonly seen by home inspectors in residential buildings, the rating of the breaker must not exceed the rating of the conductors or the wires. So the key point here is the maximum breaker rating must not exceed allowable amplicity of that conductor. So keep an eye on, so you're using 14 gauge for 15 amps, 12 gauges if it's aluminum. So kind of keep that in thought. And here is a video.
The home inspector shall inspect the service drop, the overhead service conductors and attachment point, the service head, gooseneck and drip loops, the service mast, service conduit and raceway, the electric meter and its base, service entrance conductors, the main disconnect, panel boards, circuit breakers and fuses, service grounding and bonding, a representative number of switches, light fixtures, and receptacles, including receptacles observed and deemed to be arc fault circuit interrupter protected using the AFCI test button where possible, all ground fault circuit interrupter receptacles and circuit breakers observed and deemed to be GFCIs using a GFCI tester where possible, and for the presence of smoke and carbon monoxide detectors. The home inspector shall describe the main service disconnect's amperage rating if labeled, and the type of wiring observed. The home inspector shall report as in need of correction deficiencies in the integrity of the service entrance conductor's insulation, drip loop, and vertical clearances from grade and roofs, any unused circuit breaker panel openings that were not filled, the presence of solid conductor aluminum branch circuit wiring, any tested receptacle in which power was not present, polarity was incorrect, the cover was not in place, the GFCI devices were not properly installed or didn't operate properly, and other problems related to the electrical receptacles, and the absence of smoke and carbon monoxide detectors.
Okay, we're ready to start the electrical section, which is 3.7 in the SOP. And we're here at the main distribution panel. And I'm going to take a reference photo first with cover on. I'm also going to take a photograph of the indexing that they've got here on the inside of the door. And I want to know what the brand name is of this panel as well. So I just took a picture of that so I remember it when I sit down and do my report. One thing in this panel is that there are no GFCI breakers or no arc fault breakers in this panel. Now we're going to take off the dead front off the panel. Okay, so now we got the dead front cover off. And typically the way I look at these panels, I'm going to start at the top and move my way down on each side. Check for double taps, any kind of damage there might be in the conductors. This is a sub-fed panel, which means that we've got a main that's located remotely somewhere. In this case, it's on the other side of the garage. So coming in here, everything looks pretty good at the top. Now I'm going to look for deox compound on the connections of the lugs, the main lugs, and I can see it. They've all been coated well, so there's no worries there. You see the paste up here? That's our deoxidizing compound. Prevents any oxidation, corrosion of these connection points. Also helps keep the connection points tight. Okay, moving on down here, we do have some double tapping on the ground bar. Over on the neutral side, there are none. Now typically, double tapping was allowed in certain years. So you can note this.
And some manufacturers allow it.
Yeah, and some manufacturers allow it because they've got the lugs are designed for double tapping. So now I'm going to come down and just look at my breakers, see if I have any trip breakers. I don't have any. Down at the bottom, I'm looking for missing connectors, damaged conductors of any sorts. Now I'm going to check and make sure my ground is bonded to the enclosure and it is isolated from the neutral. So you don't want to see any jumper wires or any tie bars between the neutral and the ground in a sub-fed panel. So really this panel looks pretty clean.
I like to point out that the panel is out of date by today's standards because it doesn't have any arc fault or GFCI breakers in it, but there is no requirement to bring it up to today's standards.
Well, that pretty much concludes our interior examination of the main panel. I think we're going to go ahead and put the dead front back on. And always remember your safety part of your inspections, always be very, very careful around this. This is energized equipment, and keep your clients back from this location at least 10 feet. Okay, now we're going to take a look at the main shutoff for the distribution panel. This particular main is over on the opposite wall from the distribution panel in the garage. We want to do the backhand test right away again. I'm going to open it up. And we can see that we have one main breaker in here. I also noticed right away that we've got some duct tape over some open breaker holes. So we need breaker fillers in here for safety. We're going to take a photograph of that. I'm going to take an overall photograph of the main enclosure. So right away, that's the two things I've noticed is the size of the main and the missing breaker enclosures. Now we're going to remove the cover. Okay, we're removing the cover on the main. I'm going to use the same method on this enclosure where the main is as I did on the circuit breaker panel. I'm going to kind of start at the top, work my way down. I want to make sure I've got deoxidizing compound on all of the main lugs, and it looks like I do. Not so important on this bottom one. This is the neutral coming from the meter. This is a copper. So we really don't have to have any deox on that. The other two coming in from the meter, they're both copper as well. So we can get by with no deox. Just checking everything in here is pretty simple. We've got our main feeds coming in here, and then we've got the feeders going out to the meter can. The grounding is correct. The grounding should be bonded here to the neutral. And it goes out to the ground rod and to the water main. So everything in here looks pretty good. Okay, here we are at the main service meter, and there's not a lot we could look at inside here. It's got a meter seal on it, and the power company does not like these removed. These are sealed for safety and to make sure that nobody gets in here and modifies anything. So this is pretty easy to inspect. There's not a lot really we can look at. We can check and make sure that it's secure to the wall. I always like to take a reference photo. Want to check our riser. We've got the expandable type riser here, which accommodates any movement in the soil. That way we don't pull any a part of our conduit riser out of the can. So everything looks pretty clean here. We're going to now move inside and start testing some receptacles and some switches and lights. Okay, now we're inside. We're going to test some receptacles and switches. And on this one here in the garage, the first thing I notice is the device cover is gone. I'm going to capture a picture of that. We'll put that in my report. I'm going to test the light. That seems to work fine. We're going to move down the wall here and we'll get another device cover missing on the GFCI in the garage. Take a photograph of that, and while I'm here I'm going to test. So it did trip when I hit the test button. Now we're going to reset it and it came back on. So that part looks okay. I will just say this much about missing device covers. If they're within reach of children, it's very important. It's a huge safety thing to get these covers on there. If they're in another location, perhaps on the ceiling of the garage or some other place where it's out of reach, it's not such a huge deal.
But still point it out.
But still point it out.
One more thing about GFCIs. The manufacturer's recommendation for testing it is to press the test button. Then that's the manufacturer's test, but most of us will use the 3-light tester just because that's what we do.
Now let's go ahead and move inside. We're going to test some more receptacles. Okay, so now we're going to start testing some more receptacles and switches inside the house. Before we move on to receptacles, I may want to just mention that in the SOP, it says we need to test a representative amount of receptacles and switches. What that basically means is to test the ones you can get to. That would be advisable, because you're not always going to be able to get to all of them because of bookcases, TV stands, or whatever the case might be. The same goes for windows too. There's a lot of times you're not going to be able to access a window and get it open. I'm going to turn this light on, overhead light, and there's another switch here. It's for the paddle fan. Everything looks good there. So let's go ahead and move on. I use the standard plug-in tester. It's got the 3 lights on the front. It's got the little index at the top. And what I'm looking for is potential reverse polarity, open ground, open neutral. And each one of these has a combination on here. If the 2 lights on the right-hand side come on, that usually indicates it's okay. So we're going to keep moving down the wall. This house is vacant, so we're able to go around all the walls and test them. This is actually the master bedroom of this home, and there is a master bath attached. So I'm going to just step in there and I'm going to test the GFCIs. There are 2 methods, like Lon said earlier, to test these receptacles. You can either use the plug-in tester or you can use the test button. I'm going to have to use my tester on this one, and it does work. We'll do a reset. Retest again, and it looks good. Now I'm going to move to the receptacle down on the other end here of the vanity and see if it trips the receptacle, and it does. But we've got an issue here. I'm showing a reverse polarity when I tried to trip that GFCI. You can see the outer lights are lit up. So we actually have an issue here. I'm going to go ahead and take a photograph of that. I'm going to move back to the GFCI. The GFCI shows it's dead. However, when I test the one that's on this GFCI, it showed that I had a reverse polarity. So obviously we may have some wiring malfunction here. And we're also going to test the lighting and the exhaust fan in the master bath. Everything operated and functioned properly. Now we're going to come out here to the living room area and test a few out here as well. Right here at the base of the stairway railing, we've got a floor receptacle. And in some cases it may require that you unscrew the cap. And the reason we need one here is because this railing by the stairwell is considered a wall space. So we have to have a receptacle along this wall space. I'm going to go ahead and just test one side. My lights on my tester show it's good. Now I'm going to go ahead and put the cap back on, the cover. These are dust covers. They're supposed to help keep dust and lint and so forth out of the receptacle. Now we're in the kitchen, and we have all these receptacles here up on the kitchen countertop, and I'm going to go ahead and test all these. Now the first one here is a GFCI. Did the manual test with my tester, reset, and that one's okay. We've got one here very close to the sink, and according to today's code, we have to be within 6 feet. Anything within the 6 feet distance from the outer edge of the kitchen sink has to be GFCI protected. Okay, we got that one tripped. It appears it's this one over here to the left. And both of these are on that same GFCI. I'm going to do a reset, retest there, and I'm just going to come back over here and do a quick retest here to make sure everything came back on, and we're good. When this house was built, the requirement for GFCIs was closer than the 6 feet from the edge of the sink. So therefore, these actually are grandfathered in. We really don't have the authority to make this change or recommend this change. We can recommend it, but we can't enforce it.
But today, everything in a kitchen has to be GFCI protected. But at the time when this house was built, like Ray says, this is good, we move on.
We've got a island countertop here, and according to the code at the time this house was built, there should have been a receptacle on each end of this countertop, but right now there's just one. So we would have to put this in our report that the opposite end of that receptacle, there is none, and we're going to recommend that have an electrician put one in on this end as well.
The reason we do that is kitchen appliances only have a 3-foot cord, and so we can't plug in an appliance on this end of the island without using an extension cord, and we don't like extension cords.
Okay, we've gone through, we've tested all the lights, the receptacles, we've taken a look at the circuit breaker panel, the circuit main. We're now going to conclude our electrical section, which is 3.7 in the SOP.
According to the InterNACHI Home Inspection Standard of Practice, the inspector is not required to measure or determine amperage or voltage, the main service equipment, remove the panel board cover, I've said that 1,000 times already, insert any tool, probe, or anything into the panel board, sub-panels, distribution panel boards, or even electrical fixtures, operate any electrical disconnect or overcurrent protected devices. So the inspector may choose to go beyond these standards, and which I often do, but again, this is for your safety. We got a few minutes left. So adequate space should be provided around the electrical panel board, the safety access to the components. This is one of these call-outs that I call out quite a bit. The working space in front of a panel board must be at least 36 inches. That's 914 millimeters, yes. The working space must be at least 30 inches, 762 millimeters wide in front of the electrical panel board and at least 6.5 feet in height. And this is in 1981, or 1,981 millimeters. Panel boards must not be located in bathrooms, toilet rooms, clothes closets, or over the steps of a stairway. The overcurrent devices must be readily accessible. Okay, let's see. Each circuit should be distinguished. We've got a few minutes here. We're going to keep going for another couple minutes here. Each circuit should be distinguished from all others. Spare circuits should be labeled accordingly. These should be a circuit directory installed on the face of the panel board door inside the panel door or in the location adjacent to the panel board. This requirement helps protect occupants and contractors when they're doing work and shutting off the electrical into certain parts of the house. So home inspectors may often find the panel board door with illegible markings and fail to identify the circuits specific and accuracy of those. If the markings at the breakers of the panel board are not legible, a code violation exists and the condition is a defect, needs correction. A potential safety hazard exists where circuit breakers are mislabeled, and um, that is not good for occupants or electrical workers that might be doing some work on a circuit. So because this is a safety issue, panel directories must be labeled plainly with words that provide complete and accurate descriptions of the circuits served by the overcurrent devices. Now, don't put them in pencil either. I remember that on a home improvement show. Everyone needs to realize that the time electricity is present, there is a chance of getting shocked. No matter how small power you have or at the level, you may how many safety devices are in place, you may get electrocuted. So, or shocked. Electricity needs at least two wires to work. One that carries the power to the device, which is the hot, and one that sends it back, the neutral wire. The flow of electricity is called current, and that is measured in amps. The flow of electricity that's measured in amps, and then power comes from the source, like your utility company, so on and so forth. That travels through the device to the load and returns a complete circuit in most homes. The hot wire carries about 120 volts, which pushes the electrons through the circuit. The switch is always placed on the hot side, control the flow safely. The neutral wire is grounded at the panel, so it stays at 0 volts. Most standard home circuits carry 15 or 20 amp circuit breakers. Okay, some devices can hold an electrical charge even after the power has been turned off. Okay, so when I was 13 years old, I had a device, and I always messed around with electricity and stuff. And this was just this little light, and I had it on. And so I unplugged it from the wall, and it was a fluorescent uh, place. And then I turned it back on, and my finger was on the hot side, and it gave me a little jolt. And I was like, wait a minute. Didn't understand it at the time, but I got a little shock because of that. So it's kind of a fun little story that I like to tell people, that some devices can carry electrons and cause some problems. There are warning signs that a panel board or cabinet or box of the system in general may be compromised. These signs indicate to an inspector to defer. So scorch marks on the dead front counter, rust, missing or open breakers, uh, overloaded of circuits with and excessive dust and dirt and debris. A lot of times I will find, I live in Florida, so I see geckos a lot in there, dead ones. Any signs of water inside the cabinet, that is bad news. Stay away from it. Don't open it up because that could lead to shock or electrocution. So uninsulated wires, make sure you call those out. And if you cannot confirm cabinet is not electrified. So the panel board emits a buzzing sound. I've had that happen a few times where a circuit breaker was actually out and it was humming. And when I did my thermal reading, I could actually tell which one it was. So an arc flash, these occur when a flashover of electric current leaves the intended path and travels through the air from one conductor to another or a neutral or ground. This is bad. If I were you, check it out on YouTube. They have a lot of videos on arc flashes and how fast they off. It often happens unexpectedly and it can be exploded but brief. It can also last seconds and be rather visually spectacular. It can cause a little damage or it can disable a system and require replacement of the entire equipment. An arc flash of any size is quite dangerous because the path is unpredictable. It can attract to the nearest item and greatest conductivity such as like an unsuspected rodent, a house pet, or even a person. An arc flash can cause serious electrical burns. It can be fatal electrocution, exceeding temperatures of 35,000 degrees, which is approximately 25,000 degrees hotter than the sun. So not good. I knew a guy that had an arc flash happen on him, and he got third-degree burns, and uh, not fun. An arc flash can cause serious injury or death. It can blind a person or burn the inspector. I know of an inspector that took off a panel front cover from FPU, and it actually blew up in his face. So the blast can also rupture eardrums. It can, if more than 75 milliamps of current pass through a body, it can actually cause the heart to be irregular or cause heart attack or cardiac arrest. Studies suggest that electricians that have been shocked so many times that people end up with neurological problems and other signs of psychological disorders because of getting shocked, and even memory loss has been related to being shocked. So without quick help like CPR or defibrillation, this can be fatal. A lack of oxygen to the brain for more than 3 minutes can cause death and permanent brain damage. Many inspectors never fully require or recover after such an attack. Okay, so know your limits. You don't have to open an electrical panel. I've told you that. You don't have to do it. And then wear your gear, wear protective uh, covering or PPE, fire resistant clothing. Pay attention to your surroundings, use the right tools, and keep your clients safe. I like walking clients through the inspection, but if there are any signs of danger around the panel or electrical system, I keep them back. Say, hey, just stand back there. This is the most dangerous part of my job, and I'd like you to stay safe. And that's how I kind of end that. I was talking about the precautions and stuff that you can do to keep your people safe. You can actually get these floor signs here, and you can get those at Inspector Outlet. So you can get those, and it's kind of cool. What I do is I actually put a sign on my ladder that says inspection in progress, and that seems to keep people away. So the service entrance cable, the blue arrow, is what brings power from the main disconnect into the house to the spot inside where it connects to the utility lines. The connection point is called the splice or the tap, the orange arrows, and it's where the home wiring ties into the service drop, the red arrows. Um, the over the overhead lines coming from the power company uh, right there. So you can see how it dips down, goes into that drip loop. So we want to make sure that for inspectors, we are looking at that service drop. We're looking for that drip loop there. The wires feeding into the house, and we're looking for the splices or the taps. So these are things that we're just kind of visually look at from the ground. Sometimes you can see them from above the roof there too. So just keep an eye on that kind of stuff. Make sure that it looks somewhat like this. Okay. The SE in SE cable stands for service entrance. You should know that by now. The cable is made to handle sunlight and physical wear. It's also it's usually mounted directly to the building instead of being run through conduit. If the cable is in a spot where it can get hit or damaged, like near a driveway or where a car door opens, it needs to be protected inside conduit. At the top, it should have a gooseneck or a service head cap to keep the water out. If the gooseneck is used, the end of the cable where the wires come out should be sealed with a heat shrink sleeve to prevent moisture from getting in. The cable should also be secured, fastened to the building every 30 inches and within a foot of the top of the meter. That was good to know. I feel like we've seen this slide before, right? The SEU cable is a 3-wire service cable and has 2 hot wires and 1 neutral. The neutral is usually stranded and wrapped around the cable, giving it an oval shape. The SEU cables don't have a grounding wire, which means that they can only be used up on the main service disconnect, not beyond it. because after that point, neutral and ground must be separated for safety. The SER cable is a 4-wire round service cable with 2 hots, a neutral and a grounding conductor. It's used after the service disconnect, such as feeder panels or sub panels, since it is included in both neutral and ground. Inspectors should know the common cable size, wire types, copper or aluminum, and their amp rating. In most homes, SE cables carry power from the service drop to the meter, then from the meter to the main panel. The example shown is a 200 amp panel fed by a 4-wire SER cable, where the main disconnect is located outside of the meter and another disconnect is installed inside the panel. Service entrance conductors, like all others, they are made from either copper or aluminum. Aluminum conductors need to be larger size than copper. We've talked about this for any size given amperage. So aluminum terminals may also be coated with an antioxidant. We saw that in the video, and that helps prevent the corrosion of the metal. Although the more recent AA8000 aluminum alloy conductors do not require it. So there are certain aluminum that doesn't need it and some that do. So when in doubt, further evaluation. Okay. The table shows the common cable sizes here for both copper and aluminum, together with their amplicities and wire sizes. It's a good idea to screenshot this if you can. That way you have it with you. You can always go back to it if you need to. Most homes in North America use a 120 to 240 volt split phase system. Power comes from the transformer or the utility pole and runs down to the house through a service drop. That is a bundle of wires you see overhead. It includes 120 volt hot wires and neutral wires. Sometimes there's also a messenger wire that helps support the line. The neutral wire from the pole is grounded at your home, usually by the metal rod driven into the earth near the service panel. This device or this setup allows you both 120 volts and 240 volts in your home. When you connect something between the hot wire and the neutral, you get 120 volts per side. So if you're looking at this, I'm going to kind of do this real quick. When you're looking at panels, they have 2 different sizes. This is running one hot side. This is the other hot side. When you click them together, you got, oops, okay. Can't do it. My wall's going to fall off. Sorry, but it's actually connecting both of these together. That gives you the 220. 120 equals 240. So got it? That's how that actually works. So service, the electrical service, this is the general term that's used to refer to all service conductors and equipment. The service begins at the load of the service drops, the lateral, and ends in a panel board cabinet that houses the main disconnect means. So that's basically what that is. You can read the rest of this. Overhead service, wires, and stuff like that. When you're looking at this, kind of get an idea of the basic terminology that people use. And if you're talking to another electrician or you want to sound a little bit smarter, take a screenshot of this and memorize a lot of this stuff because it can help you out. The illustration here shows another point connection between the facility and the service utility and the wiring of the house. You can look at your transformer, which actually transforms the high voltage to acceptable voltage to your house. So I have had where a customer called and said that they were getting too much voltage when they found out that their transformer was actually malfunctioning. They had to call the main power supply and they actually came out and replaced the transformer. Okay. And other structures should not be at least 10 feet above the finished grave. You can read all that. When the service drop is located above the eaves, the service mask or the riser is run through the eaves. When the run underground from the utility pole to the electric meter, service conductors are installed in the buried conduit or run as an underground service entrance cable. So that's kind of how that works. So we have an electrical pole out here, and we actually have everything running in conduit right to the house. That works. Each main service hot wire connects at the breaker or fuse in the main disconnect. This is first overcurrent protection. The main 240 volt disconnect in housing either in the panel board or in its own separate box, usually installed near the meter base. The main service ground, the neutral conductor, connects to the neutral bus bar. It's located at the neutral bus bar, varies depending on what panel you have or the panel manufacturer. It is typically a silver color with many small holes and screws and one large hole for main service ground wire. Okay. So there are, however, a few variations on the theme. It is not unusual to see one of the live conductors tied back. This is inductive of the 120 volt only supply, which is still installed in some older properties, apartments, and condos. Controversially, the inspector may see cable assemblies with more than 3 connecting conductors. This is typically a 3-phase supply commonly found in both commercial and agricultural environments. In this case, the 120 volt supply, we recommend that the inspector report show this limitation. In case of high voltage 3-phase supplies, we recommend that the inspector defers this part to an electrical specialist or a electrical contractor, just for a qualified industrial inspection or commercial inspection. Okay. Point of attachment to the building of the structure. A typical 3-wire service drop consists of 2 insulated hot conductors wrapped around the bare stranded aluminum wire with an internal steel messenger cable. The bare aluminum wire also serves as a neutral. The middle image above shows the overhead service drop and the weatherhead, including the 2 hots and the 1 bare wire. Okay, stranded service neutral. The neutral, or the grounding conductor, also serves as the main physical connection to the building there. The inspector should ensure that the strain relief is not detached or pulled away from the structure. The point of attachment of the service drop conductors to a building or structure must have a clearance above the finished grade of at least 10 feet. We saw that in the slide a couple slides ago. On some older properties, the conductors are not in an accessible, and each has its own connections to the structure. But this is rare these days and probably in need of replacement. So the inspector image at the right shows one of those older. And I have seen those, but not very often anymore. The inspector, the left and, sorry, this caught me. The inspection image shows on the left there, shows where the second story deck has been added, putting the electrical supplies too close to the walking service. The overhead service must have a minimum separation from both the structure itself and any walkways, driveways, balconies, patios, and swimming pools. Very often an inspector will see properties that have been modified and the service overhead should have been relocated, but it wasn't. This can obviously lead to some dangerous conditions, especially over swimming pools, which should be, was it 22 and a half feet above the pool. And then, yeah, it's just really not do that. I did a house in Minneapolis where they added a back porch, and when she opened up the back door, it actually hit the service wires coming in. True story. Scary. Conductors must have a vertical clearance of at least 8 feet above the roof surface with a distance of at least 3 feet in all directions from the roof edge. the NEC 230.24 if you want to check on that, okay? There is an exception for low slope roofs or flat roofs, which a surface is accessible to pedestrians such as balcony or deck. Overhead service conductors supported on or the cable together with the grounded bare messenger wire. Above a roof surface subject to pedestrian traffic must have a vertical clearance of at least 10 feet or 3,048 millimeters. The minimum vertical clearance must be at least 10 feet at the electrical service entrance to the building, at the lowest point of the drip loop of the building electric entrance, and above all areas of walkways accessed by pedestrians only. Such clearance shall be measured from the final grade or other accessible surfaces such as a deck or balcony surfaces. If it's just a flat roof and no pedestrian access, then the clearance can be 8 feet or 2,438 millimeters. Yes, I figured all that out. Another common clearance problem is caused by trees and shrubs. This may interfere with the overhead supply. The inspector should take the time to eyeball this when they're doing their inspection. From the supply pole to the attached point of the structure. The report, you should really report on all trees. I saw one that was actually, the wires actually grew inside the tree, so it was there for quite a while. Also remember that the branches are heavier during the summer and can weigh down on the conductors. What may be marginal during the winter months may cause some problems later in the growing season. The inspector should recommend that any leaves within that 5 to 6 foot around that cable should be really cut back. So that is no joke. In most cases, where the home is fed by a service overhead, the supply is fed down the outside of the house through the conduit known as the service mast. In some cases, the cable assembly is the type SE, which requires no conduit. The mast head, or gooseneck, as it's sometimes called, I like to call it a gooseneck, is at the top of the mast itself. Its purpose is twofold. First, to act as a rain cap so that moisture doesn't enter into the conduit. The second is to provide bushings to prevent individual conductors from being dampened by rubber against metal component parts. In all electrical power situations, a bushing is an insulated device that allows the electrical conductor to pass smoothly through it and safely. The mast head should be undamaged and securely fastened to the service mast. The inspector should report any of those loose fittings or cracks in the mast head and its clamps. Can't tell you how many times I've seen that, or especially after a storm. In the middle of the top picture, the masthead and service drop has been damaged by a fallen tree branch. Not only was the masthead smashed, but the neutral conductor spliced was torn apart and repaired with just jumper cables. Makes me laugh. The inspector should be reporting this. Before the conductors, after the service mast, there should be a loop in the conductors. The lowest point of the loop should be 12 inches below the point of entry in the masthead. This is to prevent rainwater from migrating up the conductors or cable assemblies and pouring down into the masthead. This is a drip loop. In the middle bottom image, it is clear that there is no loop in the conductors. In this case, it was caused by failure of the cable assembly connector of the home. So there's some cool pictures there, at least. Love the jumper cables. Love it. A mast in excess of 3 feet above the roof surface may require support. The weight of the cable assembly is considerable, and when that applies to overall tall masts, has the ability to bend right over. For that same reason, the inspector should report anything other than the cable assembly being supported by the service mast. The inspection on the left image shows tall masts that lacks adequate support. It is common to see telephone cables, TV cables, satellite dishes, clotheslines, things like that, supply to the remote building being supported by that same mast. The overhead mast must not support such things as cable TV, telephone wires, and so on and so forth. The inspector should report on all these and say further evaluation from a licensed electrician. Now, the IRC is silent in the size requirement of conduit type to be used in the masts or risers. It is also silent about the height above the roof it can extend before supporting any braces or the guy wires. In many jurisdictions, the power utility company specifies that requirement. As with other projections through the roof surface, the service mast should be adequately flashed to prevent the water from getting into the building. It is not unusual to see signs of water leakage through the roof due to poor mast flashing. Because the mast is generally outside of the conditioned space, these leaks commonly go unnoticed for years, causing considerable damage to the roof sheathing and fascia. The middle inspection picture there shows an unprofessional, unreliable repair to a mast head flashing with silicone. You can't make this stuff up. This is a common defect on a reshingle roof. It also shows a complete lack of mast head. This is a major, major defect. In the case of rigid conduit service masts, they should be attached to the structure every 5 to 6 feet throughout their entire length and should have a clamp within 12 inches of either side of the meter base, as well as the top of the mast and the projection through the roof. It is all too common to see this stuff attached to clamps, not replaced, to loose stuff on the building that hasn't been replaced. The right inspection image shows where the clamp is missing a fastener. You know, I'll give them 30 cents. Just go get a bolt for that. The clamp bolt is completely missing. Just here, 30 cents. You can fix that. I guarantee it. As previously discussed in most newer and more populated areas, the electrical supply is fed underground. The underground service conductors between the electrical supply system and the service point is called the service lateral. And if the if the utility company has an underground supply system with transformers on pads at the property line, the service lateral is that which runs underground from the house from the transformer installed on the ground. If the electrical service is overhead, the homeowner may not want service drop overhead line run across that property. In such cases, the conductors may be run down the utility pole in a raceway and then run underground to the house. Both of these installations would be called the service lateral, which is defined in the IRC, or the the Residential Code, in Chapter 35 of the 2021 IRC, as the conductors from the utility main pole at the point of the connect and the service equipment or service entrance conductors at the house. The service lateral typically terminates at the meter or the main disconnect enclosure. The service underground conductors, the service lateral, is an underground system for the service entrance conductors. For underground service, the service entrance conductors connects to the service lateral and runs to the terminals of the service equipment, likely the main service disconnect. Hopefully that was not too confusing. So it's either running underground or overhead. It's still lateral. So the direct buried cable. Normally these device laterals are buried 18 to 24 inches underground, depending on the soil condition, sometimes with type UF cable rated for direct burial. Other times conduit is used to prevent the damage that could be made of galvanized steel or gray pipe is rated for that purpose. So when the cable leaves the ground, normally it channels up into conduit, into the meter box or conductor box. So, and you can actually find these wires out if you have one of those electrical sniffers and you put a Romex wire on there and you can stick it in the ground and you can actually find where it is. So little knowledge you might use, might not. Where the service entrance cable is not rated for direct burial, it needs to be in a full conduit and must be buried at minimum depth of 18 inches under landscape and 24 inches under hardscape, such as driveways. In residential construction, there would be only one conduit. The home inspector should evaluate any signs or any visual signs, that is, above ground conduits and report any damage or open joints that would allow moisture into that assembly. So pay close attention to that. I've seen quite a bit of that in my career. The electric meter here is not part of the service entrance equipment. Its only job is to measure how much electricity is being used on that property. Sometimes a property might have more than one meter. For example, if you have multiple units, or maybe you have a separate garage that is used for workspace or something like that. The meter base is part where the utility company meter is mounted. It is the socket that that meter plugs into. Now, the main disconnect, which shuts off that power, this guy, there is no single rule. It depends on the setup and local codes. Okay, it can either be in the house or outside. Here are a few common layouts. Basement setups. I've seen these in the basement. I've seen the meter in the basement before. The meter is, I've seen it in inside, outside, and the main panel is in the basement. Wires called the service entrance cable may run through the conduit, but not always. Garage or same level setup. The meter and panel might be close together, connecting by a short piece of conduit. All-in-one systems. In many areas, especially in the US, you will find the meter, main breaker, and panel all together in one unit mounted on the outside of the house. In other setups, you might see the meter outside, where wires running inside to the main panel, and that includes the main breaker and branch circuits all there. Even though people often call it the main breaker panel, that's just a common term. It's not an official code term. And again, we're not code inspectors, we are safety inspectors. A different arrangement is where the meter and the main disconnects are both on the outside and the panel is inside. In that case, the wires running from the outside disconnect to the inside panel are called feeders. Feeders carry power from the main disconnect to the panel that contains all the branch circuits, breakers. That was a mouthful. Okay, here are some cool ones that I've seen too. You have, as the meter is rated component, as the meter is a rated component of, like any other thing, the amplicity of the meter and its base cannot be lower than the stated total available amperage. As meters have increased in capacity over the years, the meter bases have changed. The very earliest meters, such as the inspection image here, had to be separate base and were typically rated for only about 30 amp supply. Understanding meter base is an important part of being able to properly evaluate the maximum available amperage in the home, but should not be relied on completely when sizing a service. So that's analog too. All right, here's a couple other ones. This is a 60 amp round meter base on a quadruplex. There's 100 amp. You see those still quite a bit. And on the right there, there's a 200 rectangular meter base. So those are a couple different ones that are cool to look at. Here's another 100 amp, and there's a 400 amp supply split between two 200 amp breakers. So see those in duplexes. Okay, generally speaking, the difference between grounding and bonding is Grounding is a direct connection to the earth to aid in removing damageable transit over voltage due to lightning. Okay. Bonding ensures the electrical conductivity of the fault current path to provide the capacity and the ability to conduct safely any fault current likely to be imposed, and it to aid in the operation of overcurrent protective devices. Properly bonding all metal parts with an electrical system helps ensure a low impedance fault current path. The last stop on the utility distribution change before the supply goes to the building is the transformer. This steps the high voltage primary distribution down to the neighborhood to the 240, 120 volt feeds to your house. On a typical 240, 120 volt service drop, we have two underground conductors and a single grounding conductor. This means that you have to establish our own grounding electrode system at the house. The three grounding electrodes conductors coming from the main panel, one connects to the metal water pipe, another connects to the driving grounding rod, the third connects to the copper wire inside the concrete. This is critical for removing dangerous voltage imposed on the system via lightning strikes or over voltage surges from high voltage on the power lines. It's very important to bond properly. Check out that video on bonding and grounding, Electricity 101. Okay, a grounding rod, footing reinforced steel, the metal underground pipe are examples of grounding electrodes, which are metal electrically conductive terminals through which current enters the earth. So there are several methods of connecting the grounding system to the ground, with driven grounding rod being the most common in most areas. Most residential construction requires two grounding electrodes in combination of the following, which need to be driven at least 6 feet apart. Driven grounding rods, that would be the rod type grounding electrode rods, the metal water pipes, metal well casings, oofer grounds, those are going into the slab, grounding plates, steel framing, and grounding rings. Historically, the grounding system had just one connection to the ground, and this was nearly always made on the water supply pipe. However, now required in most jurisdictions to ensure low impedance ground, one uh, one with little resistance. So, however, these two connectors have to be together because most utility companies now install plastic potable wires or water supply lines. So you can't really ground on plastic, right? A water pipe cannot be used as a ground means anymore. So one of the other electrodes listed must be used. It is also important to note that the electrodes that are present in the dwelling must be bonded together to form a single complete grounding electrode system. Typically, these two require grounding electrodes need to be at least 6 feet apart. It is very important that that is actually part of that, okay? And if you want to reference that, that's at 250.56 in the NEC. Gas piping should not be used as grounding electrode for safety reasons, but in most areas, gas lines are required to be bonded to the electrical system if they are likely to become energized. Very important to know. Rods are made of stainless steel or copper or zinc coated steel, shall be driven or shall be at least 5/8 of in diameter. Grounding electrodes of a pipe and conduit must be at least 3/4 of an inch. Metric designing of 21. There are special listed rods and listed rods may not be less than a 1/2 inch in diameter. If pipe or conduit is used as a grounding electrode, it must also be no less than 8 feet in length and no smaller than the trade side or 3/4 of an inch. If visible, you may be able to confirm the diameter by looking at the listed markings, which may indicate the rods complies with the diameter required by the National Electrical Code. This listing agencies are the CSA, the ETL, and the MET, and the UL. Well, marks on it are greater than a 1/2 inch in diameter, and that will have the correct minimum amount of coating. All rods and pipes should be at least driven 8 feet into the earth. The rod and pipe must be installed at least 8 feet of length in direct contact with the soil and ground. Sometimes, now, in very rocky earth, you can be driven at an angle no less than of a 45-degree angle. Now, they can be installed in a trench no less than 30 inches deep, but no part of any grounding electrode can be closer than 6 feet to another one. The upper end of the electrode should be flush with the ground, or at least below the ground surface, so that the end of the attachment are protected from damage. If you find a rod sticking up out of the ground, that's a defect. It should be at or just below soil surface. In the image, the home inspector is looking at the upper end of the driven rod and its attachment. Pipe or conduit made of steel shall have an outer surface that is galvanized or otherwise metal coated to resist corrosion. If the material is iron or steel, the electrode must have its outer surface galvanized or metal coated for corrosion protection. Good to know, isn't it? The ground wire. The grounding electrode conductor needs to be fastened, referred to as the attachment, with the correct approval clamp. And the attachment needs to be rated for direct burial if located below ground. It is common to see these acorn clamps installed improperly, with a conductor clamp under the screw rather than to be in the solid part of the clamp, which has a biggest contact area. So connecting that, can't believe people actually do that. Anyways, connecting to the main metal water pipe in a house was the most common type of grounding at the time. The right image shows the cast bronze clamp for connecting the wire to the water pipe. Where the metal pipe is used as a grounding electrode, the conductor should be connected with clamps rated for water tubing and needs to be connected with the first 5 feet of piping as it enters the structure. Since the water meter is a removable part of the potential circuit, a jumper cable must be attached on either side of the meter, so that way if it does get energized, it's not going to blow out that meter either. So just okay, a jumper wire looks similar to either one of these. It's also used as a conductor, or also a wire called a conductor, used to ensure that there is electrical conductivity between both those metal parts. The well casing as wells are bonded to the great depth and lined with a metal sleeve. They make good grounding electrodes as long as they are far enough away from other grounds that are properly connected. So along 6 feet. I'll give you the answer to that one. With so many homes and commercial buildings now built on concrete slabs, the grounding system has become very common. The requirements for UFR grounds are that they have either 20 feet of number 4 rebarb or for AWG copper wire embedded in at least 2 inches of solid concrete within the footer that is contact with the earth. This system must also have an external means of connecting another ground system to it, which, like for your telephone lines or something to that effect. The system here, forgot what I was going to say. Forgot. Keep moving on. The inspection image here shows both the rebarb in place prior to the concrete pour and above ground accessibility connection for the grounding system. The rebarb is painted green, so it is present, can be verified by the local building inspector having authority. Okay, grounding plates, you're probably not going to see too many of these, but they have to be at least 1/4 inch wide and they should be at least 2 foot square around that. Steel framing, now steel framing buildings have to be grounded as well. And a lot of them are bonded into the electrical system if you have a steel building and electrical. I don't need to go there. See, squirrel, I'm over here. So 10 feet of connections to the earth. And then the ground rings, a lot of times these are more common like in pool structures and stuff. Although it is very, very rare to see these in residential constructions. The minimum of 2 AWG connectors is buried beneath the earth and at least 30 from the structure. So that's kind of it on that. I love this picture. The grounding electrode conductor, the GEC, is a conductor that connects the system grounding conductor to the equipment to the grounding electrode or to the point of grounding electrode system. The GEC is copper, aluminum, or copper-clad aluminum. It is not intended to carry current except in case of a ground fault. It can be bare and without color. Its size is related to the amperage of the service entrance. Okay, so the table below will show you the sizes of the grounding electrode here. Remember, the GEC should be connected only to the neutral and the service panel. The panel containing the service disconnect and nowhere else. The GEC is usually connected to the grounding service conductor, the neutral service conductor, in the service equipment where the main disconnect is located or in the meter enclosure. The grounding electrode conductor, the GEC, and the grounding service conductor are bonded together to the metal enclosure, okay, by the main bonding jumper, screw or jumping connector in the neutral bus bar. That's what this does, okay? Now, the equipment grounding conductors, the grounding wires are also brought to this point and tied to the ground service conductor, neutral conductor, and the grounding electrodes. And we are just going to keep moving on. All right. Surge protectors. Now, the NEC 285 was in 2002, the surge protector or surge suppressors are mentioned. In 2020, the article 2230.67 says it is mandatory requirement for the first time for dwelling units to be provided with a type 1 or type 2 SPD, service protector, okay, or surge protector device. So that's it. Normally there's like a little light on there and you can see that it's on. Now they got them more inside the panel. They actually snap here and they should not be double tapped. Okay. At the main service panel board, that has the initial main disconnect, neutral conductors, white wires, equipment grounding conductors, the bare copper or the green insulated wires, the metal service panel board cabinet, and the grounding electrode system must be all bonded together. The code requires that the ground and the neutrals to be kept separate except at the main disconnect. So if this is the main breaker, this will be connected. After this, they have to be separated. Okay, I go into detail about this in the grounding and bonding video I did. So to discuss between the grounding and neutral bus bars on the panel bar, the inspector can look closely at the connections to the body enclosure or the box. The panel board ground terminal bars are screwed directly into the metal body of the panel. Neutral termination bars are insulated from the panel body. Main service panel boards must be bonded to the grounding system, but there is also a very long list of components that need to be connected to the ground since they have the potential to become energized by electrical fault. These components include interior water piping, water heaters, around water meters, gas lines, electrical enclosures, electrical raceways, electrical outlets or junction box, CSST gas piping, manufacturer's compliance, of course, and telephone and cable TV systems all have to be there. We bond pipes because if it's metal pipe is energized, inadvertently a bonding jumper provides the easy path back to trip the breaker. Refer to the following illustration of the grounding electrode conductor connected to the metal water pipe near the water meter. Okay. Inspectors may observe metal water lines bonded at the water heater supply pipe and metal gas pipe that they are so close panel bar. I just butchered that whole sentence, didn't I? Inspectors may observe some of those water lines bonded at the water heater supply pipe and the metal gas pipe that are close to the panel board as possible. For a 200 amp service, the code calls for at least 6 gauge copper to bond metal gas pipes and 4 gauge copper for water pipes. Yeah, sorry about that. At the main service panel, there are 2 hot wires coming from the connector to the main breaker. That would be these guys right here. Okay. The neutral wire connects to the neutral bus bar. That would be this guy right here. Okay. The neutral bar is bonded to the metal box using a special screw or strap from the manufacturer. This is called a main bonding jumper. Okay. I don't, that should be like right here. Oh, here it is. That's where it should be. I don't know. Can't tell. I think I threw it away. So, anyways, the MGB ties everything together. It connects the neutral and the grounding system, so it includes the bare or copper grounds wires at the service panel to itself. The connection keeps all parts in the same electrical potential, helping ensure the system's safe and grounded. So it's going to send overcurrent somewhere else. The factory supply bonding jumper strapper screw is shipped directly as the loose components because the manufacturer doesn't know how the panel will be used. If it is used as a service equipment, main panel, that is, the neutral conductor bus bar must be bonded to the enclosure. If it is not used as such, then it has to be isolated or separated from. The inspector image shows several types of panel board bonding. Some are straps and some are screws. So I'll give you a few seconds to kind of look at that. See a little bit of overcurrent there on that one picture. If the ground fault in the house, the MBJ ensures the current can be safely directed to the ground, away from the house and the people inside. The MBJ provides a low impedance fault current path back to the power supply to facilitate the tripping of the overcurrent device in case the ground is fault. Grounding is the single most important component of a building's electrical system, and the MBJ is the single most important connection in the entire electrical system. In modern electrical panels, the bonding connection is usually made with a green bonding screw. This makes it easy to spot. So when you see that, the electricians, the inspectors, the code enforcers can see that a lot easier. In the main service equipment and only there, the neutral and ground wires are connected to the same bus bar. I think I've said that 1,000 times already, and so you know, main connected, outside, going to be disconnected. In the setup, the neutral bus bar acts as the main bonding jumper because it ties the neutral and the ground systems together. They're symbionts. Inside the main service panel, all the ground wires attach to the grounding bar, which is bonded to the main cabinet through the MBJ. So from the same grounding bar, a large bare or green wire of the grounding electrode conductor, the GEC, runs out and connects to the grounding electrode. That could be the ground rod driven or the OOFR or whatever it is, or the 20-foot section of rebar. Okay, so hope y'all are getting this. At the main disconnect, all neutrals and grounding wires are combined and connected. I think we keep going over this again because I want to get that in your head. In addition, distribution panels, the sub-panels, the neutrals and the grounding wires are not combined. And the green screw, if present, should be screwed down. Take a look at this inspection image here. Again, in the green or MBG is properly not screwed down at all. This is properly installed because the panel is a sub panel, not a main service panel. But you might want to put that in as further evaluation, just in case. Just my thought. So there you go. A service panel board is a distribution or load center that contains the main disconnect. Means the main disconnect breaker, for example, this is only panel where the neutral and ground should be joined, bonded together. Distribution panels or load side panels are downstream from the main panel containing the main service disconnect. In these panels, the neutral and ground should be separated and the neutral bus isolated. The only exception is the only exception to this is existing detached structures where no metallic parts exist between the structure. In this exception, a connection between the grounding conductor and the metal case via bonding jumper is permitted. So according to the 2008 NEC, this is not allowed in new construction. So in all cases, a 4-wire feed to the detached structure is required in order to isolate the grounds conductor and the equipment grounding conductors. There are 2 different types of feeders, R4 and 3 conductors. Each are allowed in the code book under 250.118. 250 in the NEC is all about the grounding and bonding. So when in doubt, the best way is to check the codes in that section for reference. Every structure is required to have a grounding electrode system. If they are present in the structure, they must all be bonded together. In a detached structure has a remote distribution panel located in the structure, then it requires a grounding electrode system of its own, 2008 NEC. The equipment grounding conductor in a 4-wire feeder does not take the place of the required grounding electrode, and that's in the NEC 250.32B1. It is also important to understand that if the detached structure is being fed by a single branch circuit and it contains an equipment grounding conductor that is used for grounding and non-current carrying metal parts or equipment, then no grounding electrode system is required. The inspector should pay very close attention to the grounding and bonding of all electrical circuits. Sometimes it is very hard to figure out which components are electrically connected to each other. When in doubt, I always recommend a licensed electrician for further evaluation. Always a good idea. Okay, we are going to watch this video.
Different types of grounds.
All right, guys, let me start that over.
Different types of grounds I'd like to talk to. In the Chicagoland area, we use water pipes. and think about it. You got miles and miles and miles of underground steel, lead, copper, unlimited pieces of metal that's underground, which are fantastic conductors and are going to allow everything to flow quick and easy. We're still going to be limited. All right, that's still going to only limit 5 amps of electricity to flow because it still has to get from that over to the transformers. So getting from those 2 points is where our resistance is going to end up being. All right. Yeah, there's just not enough electricity to flow to clear the path. All right. Different types of grounds. Let's go back to this one here. And different types of grounds that we're going to run into. So here it mentions the water pipes. We already talked about the ground rod outside. Some areas of our country, they don't have soils where they could dig into. Sometimes they're on bedrock and they can't take that piece of steel in there. Sometimes it's going to be on a slab. Different things that we can use for a good connection to the earth, item to earth. Well casings. All right. So if I got a metal well casing that goes down, I could ground to that. I could do something called a ground ring. So I would end up taking a number 6 or a number 2, depending on the size of the electrical system, and it would be a bare copper wire buried about a foot underground going around the entire perimeter of the house. That's called a ground ring. A ground plate is basically a 4x8 sheet of metal laid flat, covered in dirt. All these are good connections. An oofer ground is another one. That's where I use the steel rebar that's in the concrete, and I'm going to use that as my connection to the earth. All of those are acceptable, all right? And all of those are going to help me dissipate lightning strikes, and then they're all going to also help me maintain that zero potential. Bonding, on the other hand, we talked about item to item. When we talk about the main bond, all right, or, I hate to do the quotation mark thing, but when we talk about the bond, that's going to be located at the first means of disconnect, all right? That bond is going to be connecting 2 distinct items. So we said bond is item to item. When we're talking about the bond or the main bond, we're connecting the grounding system to the neutral system. We're doing that so that if I do get a ground fault anywhere, that's going to allow free flow electricity, and we're going to basically change it into a short circuit, and that's going to be tripping the breakers. Without that bond, we're just going to be flowing electricity into the earth. We're not going to have enough flow to go ahead and trip the breakers, so that bond is vitally important. When we open up our panels, the first thing that we're going to look for is the bond. I want to verify that I got my ground connection to my neutral connection. That's how I know that if there's any wires that come loose anywhere that I can't see, at least I got some sort of a pathway, maybe. That I have a pathway at that point in time to get it onto the neutral system. After that, the next thing I'm going to be looking for is my grounding electrode conductor, all right, or my GEC. That is also known as my ground wire, but that's a specific ground wire, all right. That's going to go from the location where the bond is to wherever I'm going to be grounding this to. So whether it's a ground rod, whether it's a water pipe, ground ring, oofer ground, ground plate, well water pipe going in there, whatever I'm grounding my house to, that GEC is my connection from the main, where the main disconnect, it's my connection from there to whatever I'm grounding to. That grounding electroconductor does have some specific rules to it, all right? And I don't have them written down. So if you have a pen and paper, I would suggest that you write the following down. I'll try and go a little bit slow. Depending on the size of the electrical system, tells me the size that GEC needs to be. GEC, grounding electroconductor, all right? If I am less than 150 amps, then that could be a number 6 copper wire. Less than 150 amps, a number 6 copper wire. Greater than 150 amps, it needs to be a number 2 copper wire. 150 amps or more, I should say, it needs to be a number 2 copper wire. That GEC is not allowed to have any splices in it whatsoever. All right. So when I identify it and I follow the conduit or I follow the GEC going wherever it goes, I want to make sure that it's not cut and I don't have 2 connections under a mechanical splice. I'm not allowed to do that. There is one way or one type of splice that I could do. It's called a pressure splice, and they'll put a hydraulic tool on 2 pieces of wires and they'll squeeze the living daylights out of that thing until they meld it into one wire. All right. So there's no screws, there's no mechanical connection. They just squeezed it and basically made it into one wire. You would have to literally cut it with cutters in order to break that connection again. So if we could break a connection with the screw, it's wrong. If we have to cut it, then that splice is okay. And those splices don't have to be in a junction box. So as I follow that out, if I run into a junction box on my ground path, I should be suspicious. And those are going to be the areas that I'm going to open up. And if you get inside that thing and you see your GECs are spliced together, that's a problem because we're not allowed to splice those whatsoever. All right. They have to be, if they're going to be in conduit, they have to be in conduit by themselves. All right. We can't use that raceway to share with other electrical wires. They have to be standalone all by themselves. So if I'm having trouble finding my GEC and I'm inside the panel, one of the things I could look for is in my conduits, there should only be one, maybe 2. You know, if they go one to the water pipes and one to a ground rod outside, I might have 2 of them. But they should be one wire inside that conduit all by itself. All right. If any other wires do share and go in there, that's going to end up being a problem. Nothing else goes in that GEC by itself. If the GEC has insulation on it, all right, then that should have a mechanical connection because we want to use the conduit as well that protects the GEC. We want to use the conduit as part of our grounding system. So we need to have a mechanical connection pretty much at both ends to the conduit. If it's not does not have insulation, so it's a bare conductor for the GEC, and you will run into those are not required to have a mechanical or a metal connection at each end, so we don't have to tie it to the conduit. It makes sense because obviously if it's bare through and through, then most likely it's going to be touching that conduit in multiple places that comes in there. So no splices, number 6 or number 2, 150 amps is my line in the sand. Nothing else shares in the conduit with it. In Chicago, we have something called a Chicago ground, and they did that in a lot of the suburbs around here as well. So they'll come out of the electrical box, usually at the first means of disconnect, and they'll go to the closest water pipe. And when they get to the closest water pipe, then that's where they're going to attach their ground system or grounding electroconductor to that water pipe. From there, I need to follow that water pipe until I leave the building. If I have any sort of dielectric unions, or I'm switching to plastic pipes or something like that, I've lost my grounding connection. So I have to have jumpers over those if need be. When I get to the water meter, I want to make sure I'm jumping over the water meter as well, because there's going to be a time when the water meter might, if the house gets foreclosed and the water meter gets removed, we don't want the person who's going to be connecting it together. They're going to touch one side that's going to be 0. They'll touch the water main that might be something different. And once they touch those 2 different objects, if they're different potentials, then that electricity is going to flow through them before they put it together. So we need to have a jumper cable that's loose, connected. When I say loose, I mean the wires aren't wrapped around it really tight. The connections are tight and secure. We should actually be moving those to make sure that they're tight so that I know I got a good connection between the between both sides of my jumper cable. All right. Ground bounded to neutral to go ahead and clear the fault path. Good. So there's our bond screw, and these are just different examples of what we're going to see on the bond. And again, we're tying right below that. It's going to be my neutral bus bar. All right. So this whole thing over here is my neutral bus bar. And there you can see where my bond screw is. So that screw goes through that metal bond or metal bus bar. It goes through the black plastic insulation right there, and it ties into the metal box that's behind it as well. Now that metal plate runs behind the neutral and the energized conductors, and then it also ties into this neutral bus bar on the left-hand side. That is my bond. So if anything energizes my grounding system, that's going to allow electricity to get over to my neutral system, and then I'm going to have free flow electricity enough to go ahead and trip my breakers. This is known as a bond screw. Sometimes we're going to see a bond strap in here as well. That's this item down here. So that bond strap, again, goes into the neutral bus bar, ties to my box. Any electrical wires that come loose and energize, I see that, Mark. I'm going to bring that up in a second. Anything that's tied to both, anything that ties to both again are going to go ahead and connect it. So if any energized conductors come loose, energize my box, then that's going to go ahead and energize my neutral wire.
Most electrical panels used in a single phase or two family home come with a factory already built into the metal cabinet. In the article, NEC 312.2, they say panel board. I'm talking about both the panel and the cabinet together. They have to be bonded accordingly. Panel boards are rated by how much current in amps that they can handle and how many breakers they can hold. By code, every home must have at least 100 amp service. NEC 230.79C. Most modern homes now are about 200 amp panels, and it holds about 40 breakers or so. Panels are typically installed as close as possible to where the main comes into the house, and it is normally on a mounted sheet of plywood. The plywood gives a flat surface for the mounting the panel and makes it easy to staple and secure the incoming cables within the 12 inches of the box like it is supposed to. Now, most inspectors, including myself, have a mental checklist when it comes to inspecting panel boards. So I won't be going through that depth, so because of time restraints, but go back to Electricity 101 webinar if you want to know more. Common types of panel board with the integrated main service disconnect. For these panel board installations, there are 3-wire service entrance conductor cables from the meter to the main panel board. The cable has 2 ungrounded or hot conductors and 1 bare stranded ungrounded neutral conductor. If the main service disconnect were installed at the meter outside, there would be a 4-wire SER cable from the meter to the panel board. The service panel board shows how the panel bar here shown will be at the only point in the electrical system where the grounding wires and the neutral wires are bonded together. As you can see, that one almost looks like this one right here. So for commonly installed 200 amp service, the SEU service entrance cable between the meter base and the main electrical panel board will have 4 aluminum conductors for the hots and a bare 2 aluminum ground or neutral conductor. Okay. The main lugs or the terminals are where the incoming power connects to the panel and gets distributed through the home. In most setups, the main service disconnect, the big main breaker, is built into the panel and serves as the first level of overcurrent protection. Each hot wire connects to the main bus and so on and so forth. And usually it's a large 240 volt switch at the top, like this one here. The neutral wires then connects to the bus bar and so on and so forth. Okay. In the NEC, the 230.70, in the main disconnect outside or inside the home, the minimum height varies in jurisdiction. It has to be readily accessible. 404.8 NEC, we already talked about the clearance in those type of areas. So, and we've kind of covered everything that this is talking about. Make sure that that's one of my big call outs in a lot of home inspection is that there's not enough clearance around this. This would not be acceptable if this was mounted here because I have this in the way. I don't have my 3-foot clearance. So a person must be able to turn off all the power in the house with is minimal motions of the hand. And it says 6 motions in is what's recommended. The for new construction, the main breaker is normally located outside. Multiple service disconnects mean should be grouped together and marked. So most electric services will have a single main disconnect, means outdoors, just in case something bad happens, you can shut that off in a really quick hurry. So, and that's what we want to see. Okay. The hot bus bars are the metal bars. Okay, that would be this stuff right here. Okay, don't touch this. If you touch that, you're dead, just FYI. Okay, mounted to a plastic. These are plastic insulators behind there with the channel electricity clips on the back and the branch circuit breakers. Each of the 2 conductors feed one side of the hot bar in each section. So that's why it's doing this one comes this way, this one comes this way. That's why it clamps in here. It connects both these together, 110 plus or 110 plus 120. Can't do math right now because we're getting to the end of this. So that makes it 240. Sorry. Okay, the neutral bus bars are typically strips of aluminum bored holes into the secure and connects the wires, acting as the hub. That would be this here, and this is actually connected to the grounding too. So at this point, the grounding bus bars are centrally safe. A lot of times you'll see something like this and it will be up here or down here and it will be attached or it won't be attached to this. And that is common practice throughout all of America, basically. The main electrical service panel board with the integrated main circuit breaker disconnect will be the only point in the electrical system where the ground and neutral bar bus is combined. I keep saying that over and over again. I want you to make sure that you get that in your head. Now, here's some interesting facts here. In 1960, the invention of circuit breakers and panels were patented and they were patented in 1910, introducing to replace those fuses. However, it is unusual to see the residential breaker panel from before 1940. Prior to this, electrical breakers were primarily used in manufacturing and naval applications, believe it or not. Breaker panels started appearing in homes in the mid 1950s in small numbers and were universal in most of the areas of the United States and Canada by the 1960s. Circuit breakers did not replace fuses due to deficiencies from older technology. The problem was that when a fuse blew, a person would just had to find a replacement. Breakers were obviously more convenient because you didn't have to go find that and replace it. We now have added benefits of circuit breakers with the invention of like the ground fault circuit interrupters and the arc fault circuit interrupters, which really made it a lot more convenient. Circuit breakers are the most commonly used for overcurrent protection in residential wiring throughout the whole world, basically. Code requires that the overcurrent protected device, like a circuit breaker or fuse, be installed in series with each ungrounded conductor, the hot wire, at the point where the conductor receives its supply inside the panel board, okay, except for service entrance conductors. So circuit breakers fall into 4 categories. You got the 240 volt double breakers. That would be this guy right here. The one single volt is this one right here. Okay, now I won't be able to get that back in. The GFCI breakers that were introduced in 1970s and the AFCI breakers that were introduced in 1997 and became code in 2002. Okay, the 240 volt system has 2 handles and move together. We've just seen how I just did that and it clips right into place when you're doing that. And these are called tandem breakers. As you can see, there's 2, which means tandem. And I always think of like the tandem trailers. Okay, for that reason, all breakers supplying the 240 volts are required to have their handles tied. So this has a handle tie on it. I can actually remove this handle tie, but then it becomes 110 or 120, 120. So that's why you get the 240. The breakers are molded with this connection in place, and sometimes they are linked by a listed handle tie. The inspector should ensure that the tie is present and has not been damaged. The 240-volt circuit breaker also acts as the main disconnect means in modern panels, disconnecting all electrical power. Common in the 120-volt circuits are fed from the bus bar only. Also in use are tandem breakers, which are 120-volt breakers that feed two separate circuits, which control by its own handle. These should not be linked. As with fuses, the inspector should check the rating of the breaker does not exceed the conductor size. So we know that. Ground fault circuit interrupters, the GFCI breakers, are one of the ways to protect circuits from people, protect circuits and people, not from people. That too, I guess. Not all circuits are required to have GFCIs, and in homes that are located that require this protection have their own GFCI receptacles. However, if a GFCI breaker is installed at the panel board, it will provide protection to all the receptacles downstream from that breaker in the branch circuit. It makes it a lot easier when you're an electrician too. And that's all found in the NEC in 210. Okay. Arc fault circuit interrupters, like I said, they're when they're modernized in 2008, 210.12 is where they were put in place, and they're really great until they're not. It is likely that many more locations will be added on as the NEC is um, goes forward, because a lot of people are using more electrical devices and stuff, and we're actually using more electricity now than we ever have. It is likely that these locations will have more GFCIs and arc faults, and they will be combined and things like that. The inspector shows an image of a pair of AFCI breakers. Notice the test buttons. They are also the second conductor that connects the breaker to the neutral bars. This is not a double tap. Some earlier square D AFCI breakers had to be recalled due to manufacturer defects, just FYI. Currently, however, many AFCI manufacturers are in the multi-year generation and are providing to be worth every penny, saving lives and property. It is recommended that you do check those when you're doing your home inspection, but it's also important to tell your customers check those at least a couple times a year. I always say when you're changing out your smoke alarm batteries. So the inspector should pay attention to the following questions and report any defects as need of immediate repair. Does the breaker exceed the capacity of the conductor? Does the breaker have multiple incorrect double taps? Do the 240-volt breakers have the handles tied properly? Do the GFCI breakers work properly? Do the AFCI's breakers test and reset properly? Is there any signs of overheating, arcing, smoke damage, or um, on or around those breakers? Note, the GFCIs and AFCI breakers will always be about 5 to 10 degrees hotter than standard breakers due to their internal circuit board um, way. So when I do my thermal readings, I always take a thermal reading of it, and you can actually see them a lot hotter. Now, all electrical systems require a means of disconnect. We've talked about this. And remember the SOP, the standard of practice on www.nachi.org/SOP. The inspector is required to inspect the main service disconnect. And I'm going to say it again. You don't have to open up the panel. The inspector shall describe the main service disconnect in amperage rating if labeled. Sometimes it's labeled here, not here or here. Sometimes it's labeled on top. Sometimes you can't find it. The service equipment is necessary equipment. Usually consists of a circuit breaker, switches, and fuses and accessories connected to the load end of the service connector to the house. and is intended to constitute the main disconnect means for service. This disconnect means for the service should be located outside or inside as close as possible point of entrance into the service conductors that are coming in. The service equipment should identify and markings as a service disconnect. A common service size for a single family house these days is 200 amps, but it has to be at least 100 amps. Okay. There are different types of disconnection depends on the age of the property. Here's a couple. There's a knife switch on the left. I love that little thing. It says Dr. Frankenstein, but if you know what the movie that's from, that's Dr. Frankenstein, not Dr. Frankenstein. Okay. You got the breaker style, which is most common now, and then you got the fuse links, which are were very common back in the day, and you'll still see these from time to time. In many homes and in nearly almost like all mobile or manufacturer homes, the service disconnect is not in the main distribution panel. This is not a problem, but care must be taken to fully understand the grounding and bonding of all the downstream distribution panels. In terms of grounding and bonding, the neutrals and grounds should be bonded, connected. We've talked about this. Remember that the panel with the main disconnect is the service panel, and the panels downstream are the sub panels, or service panels are distributed panels. Neutrals and grounds should be bonded together only in the service panel. Remember that, and try to remember that throughout, depending on the year of the house, because that has changed over the years. It was acceptable years and years ago. Now, for houses serving one family, the electricity should be 100 amp. We talked about that. According to the home inspector's standard of practice, the inspector shall describe the main service disconnect. We've talked about that. Any older homes may not have enough power for a modern family. Second, many insurance companies will not insure a property less than 100 amps. So kind of keep that in mind. When homes were first wired for power, they were few electrical devices, just a couple lights and so on and so forth. So a couple of a 15 amp lighting circuits and maybe a radio clock or something like that, where everybody gathered around. Obviously, in modern times, since 1960s, we've gotten much more power hungry, I guess. I mean, right here, I got 3 screens that I'm looking at. So, in many cases, the listing information about the home may not be correct regarding the service amperage because brokers or owners rely solely on the size of the main breaker or fuse. Many people are also under the mistaken impression that their total availability service amperage is the total of the individual breakers or fuses in the panel. So if I have 20, 20, 20, 20, 20, add those all up, that's not right, because it's only going to go to the 200 amp that's coming in here. And if this was a sub panel connected to a 100 amp service, that 100 amp is the lowest, or that's when that's going to trip, is 100, not the 200. So kind of keep that in mind. One way a home inspector can help communicate the available amperages to determine the amplicity of the lowest rating or the weakest link. Okay, service supply, the service meter, or the conductors, service disconnects, things like that. Here's a couple examples. A home inspector should describe that the rating. The home inspector may also describe the 60 amp meter as potential indication. That's why I showed you those pictures earlier. The home inspector is not an electrician, and we must be careful in describing the total amperage service supply to the house. Follow the standards of practice, and use words like "it appears to be" instead of "this is 60 amps." No, it appears to be 60 amp service. So your wording can really help you in that. Okay, the three, depending on the time, we're gonna kind of go through this a little quicker. So the 3-wire SEU service entrance cable runs from the meter outside the house into the main panel board disconnect, the neutral wires. Then it goes into a 4-wire system downstream. Now, a common layout has the meter outside and the main disconnect on the inside. In this case, the service entrance wires run from the weatherhead through the meter and into the main disconnect. If the meter and the main disconnect are in the same enclosure, then the wires simply run from the weatherhead to the combined meter and main direct. Okay. Now, a new panel board should not exceed 80% of its full capacity. So if I have a 200 amp, uh, yeah, I won't go there. However, an older panel board may not have room for additional circuits, and the sub panels may be added. Sub panels or additional distribution panel boards are typically powered by double pole breakers in main service panels with 4-wire SER feeders. A lot of times you'll see people that will actually put these type of breakers in, which are called, we used to call them cheaters. And you can see the different size, but you can actually put two side by side together. And that it can give you a little extra room, but it's not always the right way to do. So in the, let's see here, sub panels or additional distribution panels can have the grounding conductors, the neutrals, and the equipment grounding conductors, the bare wires, um, terminate together. The grounding conductor, the neutral, and the grounding bare wires must be separated in the sub panel. I keep going over that and over that because I need to get that drilled in your head, because so many times I've done inspections on houses where other home inspectors didn't even mention it. My house was one of them. But again, our house was built in the 1980s. So electrical panel boards, regardless of the purpose, could be inspected for the following safety related issues. Any deficiencies should be reported as need of further evaluation from the correct licensed professional. So the following related, you can look at all that: missing knockouts, missing the bushings, moisture intrusion, contamination, the rust, the signs of arcing, the even listening to it and hearing that, you can learn about that. Signs of overheating, incorrect dead front cover screws. I call that out a lot. A lot of times, like they'll have you want to you want a screw that doesn't have any points to it. So I always call those out. Missing breakers, identified labels, things like that. I mean, make it professional. All electrical panels must have adequate workspace and safety. Like I said, here it would not be adequate safety area. I mean, I couldn't work on this here, and it doesn't give me that 3-foot clearance. So the home inspector may observe things, especially like in your offices, in basements. I've seen a lot in basements when I was in Minnesota, but not so much in Florida. Uh, one time I saw a couple in a bathroom that was kind of interesting. The guy actually built another room and then but as far as the house was built, codes back then were so much different. A lot of times they put them over washing machines, over sinks. It's just crazy things like that you'll see. So the knockouts and connectors, you have to get the right, uh, make sure that it's safe. That's the basic fundamentals of electrical inspections. Make sure that it's safe. Getting the right connectors in there, making sure that you're getting those plastic pieces in there. Can't think of what they're called all of a sudden. I just ran a blank. The knockout covers. You want to make sure that all that stuff is put into place, because if a little kid walked in here and touched here, I mean, they're dead. There's no two ways about it. They're dead. Um, they might be alive, but they're going to be hurting. And you can tell by the earlier slide that I have about things that can happen to children and other adults if something like that happens. We want to make sure that we're looking at the double taps. Even double tap neutrals and grounds are very good to call out. I can't say good to call out, but they need to be called out, because what happens is one might expand a little bit or shrink a little bit, because we are looking at double taps or double lugging as a potential to have an arc. And the problem here is that each conductor will have just enough contact to cause heat, and it could arc, it could cause fire. So most circuit breakers are designed to accept only one wire. There are a few that do accept two or more. And a lot of times if I see them, I make sure I take a picture of that circuit breaker. And normally it's like rated right here. And I just take a picture of that saying two wires, blah, blah, blah. The top middle inspection image shows square D, and those are the ones that have the two wires, I believe. I can't read it, tell you the truth. Oh, yeah, I can. I got to go over on this side. Like I said, I got three screens here. So some breakers do accept those two. And the primary reason for double lugging or double tapping, was never really permitted, but it was accepted for many years. And then all of a sudden people realized that it wasn't a good thing to do. When I was an electrician, we actually did it quite a bit. So now I know better, and now I call it out. So there you go. The grounding conductors, commonly called neutrals, are and will is where our white wires inside the residential electrical panel board. Only one neutral wire is permitted to be connected under a lug and a neutral bus bar. Refer to this illustration here. Panel board neutral bus bars are usually not listed for more than one wire per terminal, okay, or fastener. It is sometimes said that the double lug neutrals are not prohibited by the National Electrical Code until 2002. This is an incorrect interpretation of the NEC. Until 2002, the NEC simply stated that panel boards must be uh, installed according to the laboratory, the underwriter's laboratory. So whoever designed this panel says, oh yes, you can put two in there. Well, the NEC was never allowed double tapping or double neutrals of lugging of neutrals, but it wasn't addressed till 2002. Wires in the panel must be correctly designed for their use. A white wire cannot be terminated or connected to a breaker unless it's permanently marked. So a lot of times you use this thing called black tape. Works pretty good. Or you take a black permanent marker. Okay. Those things can really actually save your life, especially if you're working in panel boards and electrical and stuff. Looking at the table here, we see the 12 gauge wire is a minimum size for a 20 amp breaker. The wire gauge is permitted to be bigger than a 12 gauge when connected to a 20 amp breaker. A 10 gauge wire is the minimum for a 30 amp breaker. Now there is a variance there when you're dealing with air conditioners, because they can actually be undersized as long as it doesn't go to the minimum amp size. And that's totally different. You can see that in the NEC. I think we have a, let's see. I think we got something in there. Can't think of where it's at in the NEC, but it is actually approved for that specific incident. So there we go. Let's watch this next video because I actually love this video.
Hey, Heath.
Hey, Kevin.
Wow, the professor is in. Look at your display here.
Yeah, I figured it was about time to have a little lesson on wire size, or the American wire gauge that we see a lot.
American wire gauge, that's what that stands for?
AWG, yeah.
That's funny, I always thought it was just AUG. Okay.
So you can see we have a lot of different sizes, and there's a lot of different reasons for having these. It depends on what a device is going to utilize as to how big the wire is going to be, how much power it needs.
Right, so not all electricity is the same when it's running through our house?
Right, we can't just run one size wire to feed everything in there.
Okay.
So it starts off with these smaller numbers, and it actually runs backwards till it gets to a certain point down here, and then it starts climbing again.
So let's start with the smallest.
So this is 18 gauge, and in this case it's a thermostat wire, and we have 4 conductors, but each conductor's 18 gauge, so that one right there is 18.
Okay, so something like that used for thermostats doesn't require a lot of power.
Right.
Sufficient.
Control.
All right, moving up from there.
So next step is 14. This we'll see a lot in the house, and the color kind of helps us identify it in newer homes. This we're going to see for loads like lighting, bedroom receptacles, that kind of thing.
Basic, predictable,
Right.
no problem.
Yep, and you can see it's a little bit bigger than that 18.
I have heard you throw around 14.2, 14.3. That refers to what?
So that refers to the number of conductors. So the first number is the gauge size, that 14 that we can see. But then the 2 would be we have 2 conductors and a ground. So 1, 2, and our ground. That's our 14.2.
And so there might be a third conductor if you have that three-way switch or something like that.
Exactly.
But it's still the same size.
Same size, just more conductors in the jacket.
Okay. Also familiar with this. You seem like we always run that in the kitchen and other places.
Kitchens, your washing machines, sometimes in the basement, bathrooms. We want that larger size, that 12 gauge that can handle 20 amps.
Because we're going to be using appliances that pull more electricity, a dishwasher,
Exactly.
a blender, something
So those
like
are the areas we're going to have coffee makers, toasters in the kitchen. Needs a lot more power. Want to have a larger cable that can handle that.
We've talked about GFCI receptacles before. They always are attached to something like this. Just out of curiosity, do we ever put a GFCI protection on this? Or
You can if it's providing power for something in the garage, in the basement. Absolutely, there's no problem putting a GFCI on that.
Cool. Okay, so moving on to the orange.
The orange, 10 gauge, 30 amps typically in a residence. Dryers, maybe your outdoor air conditioning unit, maybe a small oven in the kitchen.
Stuff that you know is going to pull a lot of
That's
electricity.
going to draw a lot more, correct.
So let me just ask you, what if I start using the wrong wires? Or what if I start trying to plug things into maybe the 14 gauge that I shouldn't?
That shouldn't.
Yeah.
So what's going to happen is certain appliances use a certain amount of power. So if something's really designed to be used in a kitchen or a bathroom, you want to try and plug it in there. If you try and plug it into a bedroom circuit that's a little bit smaller, it may draw too much current. It may overheat the wire, may draw too much for the breaker and cause a trip. We don't want to have an overheating issue where we're plugging something into the wrong place.
So don't bring the blender into the bedroom?
Please don't bring it to the bedroom.
Okay. This guy here?
So that's our 8. We're going to see this maybe for some smaller ovens, air conditioning units, that kind of thing as well.
Right. And then 6s?
This might be one of the last ones you'll typically see in the basement of your house if you're looking around or if you open up some of the walls. We're going to use this for an electric oven, maybe a level 2 car charger.
Gotcha. So that means that from like this point on, this is sort of more big boy stuff here?
Right. Now we get
professional
into
and-
the single conductors, and this is where we're going to install these, typically in a conduit, use it for a larger load. Maybe we're feeding a hot tub outside. Maybe we're feeding a sub panel in the house. That's where these are going to come in.
So that's interesting. You call them single conductors. So, you know, at first glance, this looks a lot bigger than this.
Right.
But to your point, there is only one of these copper conductors, so we're comparing that
To this.
just to one of those.
Correct. So this is a jacket with multiple conductors. This is just our single.
Okay. So when do we use things like this? Or this?
So this is something much larger. So something like this, or even this is 500 kc mil. This is the size. So if we really want to confuse the numbers, we go backwards till we hit 1 aught, start going up, and then we go metric.
KC, oh, the letter KC.
Yep, 1,000 circular millimeters.
Gotcha.
So this would actually carry 400 amps.
And so why would I use that?
If you had a really large residential service, I mean, it's a little unusual, more of a commercial or industrial application.
Right.
For a 200 amp service in a home, though, if we're doing copper versus aluminum, we're going to use this, 3 aught.
Gotcha. So headline here, right wire for the right usage,
Right.
for the right appliance or circuit or something like that.
And you'll be good.
All right. Well, next time we're going to talk about volts and amps, but this is enough for now, Professor.
Sounds good.
Thank you. Thanks for watching. This Old House has got a video for just about every home improvement project, so be sure to check out the others. And if you like what you see, click on the subscribe button to make sure that you get our newest videos right in your feed.
I love that video. I actually love this old house. So it was 440 on the AC. So if you want to look that up, it's in NEC 440. So that's the protection of heat pumps and electrical system. The NRC actually said something about the 3705.5.4 states that the air conditioner and the heat pump can be. So there's a couple different places there. You can also check out in the NAC 220. So to determine the maximum size of the overcurrent protection device and the minimum size of the conductors for the air conditioning and the heat pump requirement, the inspector should use the data plate. And I always take pictures of it, make sure that it actually matches, because that's just a good practice to do. So if a home inspector observes a 50 amp AC breaker on H gauge wire, that may not be a defect. It might be okay and likely not a defect. Although the breaker will be sized larger than what the inspector thinks is permanent. So if you call it out, I always say further evaluation, because some of those things, you can't know everything. And understanding, the more you know, the more you realize you don't know. Before even thinking about touching, inspecting, or removing a dead front cover, The inspector really should look carefully for the signs of water, moisture, staining, things like that. As we saw with the service entrance, any failures of the mast or cable entry may result in water getting into the panel. You may not know it until you take that water cover or the panel cover off. I've seen it where I took the cover off and there was actually water inside there after the fact. So I just took my pictures and closed it up. I also seen bees nests and everything else. In 2021, section E3404.7 refers to the interior of electrical equipment, the internal parts of the electrical, including the bus bars, wire terminal insulators, and the surface should not be damaged or contaminated by foreign materials. And that's why it's really good to, when you see rust, things like that, call that out. Just take pictures of it. Make sure you understand that this is a defect and it should be dealt with. We don't want anybody having problems. This is it can be a ticking time bomb. As part of the initial inspection of the panel, the inspector should look closely of signs along the arcing and things like that. I've seen where something blew out inside the electrical panel and was not pretty. So definitely keep an eye on stuff like that. Edison-based fuses were universal from the earliest days of electricity in the American home right up to the 1950s when breaker panels started to appear in residential construction. Many homes built until the 1960s should still have those fuse panels. Matter of fact, my last house or two houses ago had fuse panels in it. I actually liked them better, but and being an electrician, I know that it's going to blow when it blows and I'm done. So fuse panels are sometimes mentioned as being more reliable and sometimes they are. That's why they still use them in vehicles and things like that, but they are not as convenient and it's an older system. So many fuse panel or fuse type are like these block or cartridge fuses are still used somewhat. They're just not as common. Normally, you'll see them like in industrial instead of like home. But a lot of times these were installed right where your AC unit were was and things like that. And yeah, so that's how you used to disconnect them. You just pull them out. Many of the homes in the 1930s onward used main and range panels. Were all like that. I think they're cool. It's just, time has changed, and unfortunately, we don't use that, and people found a loophole and put pennies in there, and it caused some problems. So, the fuse panels may contain some of the four fuse blocks, commonly having one as many for the main disconnect too, and others supplying 240 volts. So you'll see them every once in a while. And in those cases, all the blocks must be removed to completely disconnect all the power to the home. So you'd have to pull both of those out. In other words, you just get one stream. It is common to see this. Like I said, 1950s, 1960s, you'll see these Edison fuses, and they are still common, but not as common as they used to be. These were the S-type fuses, also had the benefit of stopping someone from repairing a blown fuse. So those were the ones that people would get. And they also made ones that were kind of like your circuit breaker, so you could just push it in once it redid, but they never really caught on. And well, now when you see it, I just say, it needs to be upgraded. So there are two major problems with inspecting older fuser panels. First, check the main fused amperage. The blocks have to be pulled out, which shuts off the power to the entire house. The second issue is that these panels tend to be unsuitable for modern high amperage demands. So, and they tend to exhibit double taps and overfusing quite a bit. So, the dead front covers, screws are very important to check. And like I said before, they have to have the blunt end on there because I've had it where I've unscrewed it and blew a secret panel because obviously they damaged the wire. And it was funny because my boss was standing right behind me when that happened. He jumped. I just said, "Oh, I blew a fuse," and I just kept going. So when screws penetrate those wires, you don't want to be around for that. If yeah. scares anybody. So that's why inspectors need to be wearing safety glasses and cotton clothing and gloves when you can. So I like to use the garden gloves when I think about it. So panels, like other components, are rated for the UL listing by the underwriter's laboratory. In many cases, these panel markings are obser obscured. You can't read them. But whenever possible, you should try to take a picture of that and see if you can read some of that, because it can be very important for your customer and for yourself to know. So make sure everything is rated correctly. Home inspectors come across a lot of these older panels that are no longer available, like your Zinco panels, the Federal Pacific, the Pushmatics, things like that. Call them out and just further evaluation from an electrical contractor, because those really should be updated. And I don't recommend even taking off the front cover whenever I come to those Federal Pacifics, because I had that friend that one blew up in his face. So that's why it's really important to understand what you're looking at when you're doing these home inspections. Get familiar with these FPU, FPE panels, and Challenger was one of them too. And they got bought out, and then pretty soon they kind of faded out. The problem with the FPU panels were that they had these problems, and the bus bars weren't, it was a real thin copper, and it wouldn't sit in there right. So we want to make sure that when you're when you're inspecting these, that you call them out. I took off a front cover on FPE before I really knew that I didn't have to, and I had a couple of circuit breakers actually come out on me, and I just popped them back in place and them off. And now I probably wouldn't have done that. So, and there's 1,000 Eaton cutter panels in 2014 that were built on the Challenger design too. So there's a lot of different panels out there that you should be aware of now, but no one knows if it's working fine or not until it's under stress, and that's when you have the problems that occur. So I think we're gonna keep going here. The Zinco panels, same thing. Had some issues with them. A lot of times, if you see those colored circuit breakers, a lot of those are ones that are older and they need to be updated. And so, further evaluation from an electrician. Can't, if you feel unsafe when taking off those panel covers, I do recommend that you don't. Okay. Safety is number one. Split bus panels, between 1950 and 1980s, these panels do not have a main breaker or main disconnect. They have two bus sections, typically the upper bus and the double pole 240-volt breakers, including one that feeds the lower bus section where the majority of the 120 breakers are installed. Normally, these panels will have multiple color double pole breakers at the top of the panel, controlling the usual 240-volt circuits, such as like for clothes dryers, stoves, air conditioners, so on and so forth. When home inspectors see these split bus panels, they should count how many throws are required to turn off the panel. More than 6 throws are usually found where someone has added a circuit to a full panel by adding a double breaker, tandem piggybacking, and all that other stuff. The changes the number of disconnects throw from 6 to 7, and then that's the defect. There is no requirement to replace existing split bus panel boards. Allowed to install 120-volt breakers in the top 240-volt portion of that panel. So the three-phase supply is commonly in commercial and agriculture. Some apartment properties, you'll come across them every once in a while. These three-phase supplies have 3 hots or ungrounded conductors, and there'll be a neutral or grounding conductor. Each of these phases or legs carry 120 volts a piece, and so you can have up to 480 volts going into that. So again, these are things that you can always defer to an electrical specialist when you are unsure. Okay, that's what we're there for, is to give good advice for that next person. Okay. It is possible for an average inspector to evaluate some of the electrical branch circuits in the office and non-industrial settings, but beware of evaluating distribution. Okay. Here are some more 100+ years ago what they used. I'm not even gonna go into detail about these ones. 1920s fuses. These are pretty cool. We've touched on a lot of these. Here's a wooden box enclosure, which was really cool. I've seen one of these in my career, and it's actually plastic on the inside, so that was really cool. And General Electric made it. Some people get a little bit creative, so this is a fishing tackle box and made for electrical. The NEC requires a distinct separation of low voltage, so you should not have a doorbell inside. Um, that causes significant stuff, and you can see that in the NEC 725.16. The panel board checklist, I would just take a screenshot of this because we are not going to have time to go through all this. At least I don't think so. I'll give you a few seconds. Okay, do you want to do the video, AJ? Okay, I would recommend check out Jim. He does a really great guy. He's a great guy and he also knows his stuff. So different types of cable have different colors to them too. These are the tables that you're going to find mostly in the field. Armored cable, you got the underground feeder. I got all this stuff right here, but we don't have time to go through every single thing because we are running a little low on time. We want to check out the copper, the tin copper, the aluminum, the copper clad aluminum. These pictures really show what we can use in electrical, and every year more cool stuff is being added. The knob and tube wiring always happens between, before 1940s, and might even see them in 1945, but typically before then is when they were added in, and you'll see them every once in a while. I think it's a really cool innovation, but unfortunately they just people didn't think they were going to last. Here's some more armored cable. If you're ever going to cut this stuff, if you're kind of a handyman, cut it at an angle and it'll cut really smooth. This was acceptable for the NEC, and I still use it every once in a while too. Uh, when you're looking at cables, make sure that you're checking, make sure that there's no piercings or anything like that. You want to call all that stuff out. This is a pretty picture here of conduit. I gotta say, whoever did this made a beautiful piece of art here. That's why this is a profession, because they did a great job here bending that conduit. Let's see here. The non-metallic cable, Romex was the trademark. We talked about this. 1950 cloth covered. NM was clearly marked. Make sure that you're checking all that stuff, and make sure that you do mention that, this is older wiring, because that can cause some issues. The UF underground feeder cable, that is this stuff right here, looks just like that. Use that quite a bit. Double tapping aluminum wiring and stuff, you don't want those tied together because it can cause a dielectric there, and you need a dielectric in between there. So you can't do that unless it's just short term termination points. So just FYI, aluminum as a metal. You can just screenshot this, make sure that you check out the galvanized corrosion. You want to make sure that aluminum is great, but it wasn't the greatest property to be using, and a lot of insurance companies really frown on that now. Identifying aluminum wiring color, you guys should know what it is. Your mom probably used aluminum foil. If not you, that's what it looks like. That aluminum coir. It went all the way up to since early 1970s. I think they even used it up to 75, but typically like 73 was pretty much the likely to have 65 to 73 because of the copper scare back then. Um, let's see, option of correction. A lot of time you want to see those the crimps there, the copper, the caplonium. I can't really say that word. crimps, those are when they can tie the copper and aluminum together so that they can be a little bit more safe. This is what happens when you rewire copper and aluminum together too. It can burn out. So we don't want to see that happening. The only time that it's acceptable is like small amounts. Check out, the inspector should often see the homeowner wiring with cut down extension cords, supply circuits. I'm just gonna, I think you guys can figure this one out on your own. The yeah, that's not good. You can definitely see that there is some galvanistic corrosion there. The grayish paste is commonly found on a lot of aluminum, and just like the video was talking earlier, that should be on a lot of the aluminum, unless it's the upgraded aluminum. You don't need that anymore. So when it's permitted, just kind of keep an eye on stuff like that. You'll see it quite a bit. Since the 1980s. Yeah. Anyways, all abandoned wires should be removed. So anytime I see any wire in there, I just make a note of it. Further evaluation from an electrician. It's that simple. I've seen this happen too, where the neutral has been burnt up. And there's our timer. And then I've also seen stuff like this. Double taps, just untidy. If it's ever, it has to be tidy. That is part of the NEC. Wires should be nice and neat. That's why they do what they. Lightning damage. I've seen this actually happen at one of the houses I did. It was not a pretty picture. They had to rewire the entire house basically. Exposed wires, you want to make sure that you're calling out all exposed wires, especially I see this a lot in the attics because people don't think you're going to see it. So uh, call it out. Call it out as is. That is a hazard. I see crawl spaces, a lot of times loose wiring. You should have that attached properly, and it's really, really important that people understand that this is safety. You don't want a kid crawling underneath there and pulling on some wires and causing your TV show to go off, right? Come on. Steel studs, make sure that they have the proper insulating uh, brackets. I can't think the steel sleeves there. Make sure that they are protected. You got to have protection around those wires. I see that a lot with the conduit too, using metal conduit and then having the wires just running through there. So the non-metallic Romex cables, it has to be stapled. Carry old fuse panel box. This is being used as a junction box. Well, I would recommend further evaluation from an electrician for sure on this one. That is just, what people do. All habitable spaces are required to have electrical power. In new construction, one would expect to see an outlet every 12 feet of wall space. That includes your stairways too. Like when you have a wall up against a stairway, that is considered livable space there. So even hallways longer than 10 feet are required to have electrical power. Okay, when you have this floor mounted receptacles, personally, I disagree with the code. I really think that they should have GFCIs on floor mounted, but unfortunately, I don't write the code, but I do like the convenience of these. So the image is an approved floor box that is mounted hardware. So there you go. Service locations and kitchens. This is really important. That was what I was looking up earlier, was section 250, or sorry, 210, 52 for the kitchen islands and things like that, because somebody had a question about a refrigerator. This here is pretty important. I am going to say this. I know we're running pretty short on time, but this was common misconception that no switches could be within 3 feet of a bath or shower enclosure. This is correct for Canada, but it wasn't a requirement to the United States. But in 2023, the section 406.9C, the electrical does mention that the zone is changed from 3 feet horizontal and 8 feet vertical. So that would be considered a problem. There must be a minimum of a 20 amp circuit within 6 feet of the appliance location. Just dryers, outlets should have a 4-wire 30 amp minimum supply on it too. So that would definitely be a call out. Whenever in doubt, call it out and just say further evaluation. This definitely, you don't want to see stuff like that. Call that stuff out. Make sure that you're doing it. If you see something like this, I've seen this happen and not fun. Call that stuff out. Say, further evaluation. Same thing with if you see burnt marks on a kitchen counter. I've seen that quite a bit. Uh, Other warpage and things like that. Call that stuff out. Make sure that you're keeping an eye on all the stuff. And this is the false ground. A lot of times you're not going to see this because your tester is going to say that it's okay. You don't have to take every single electrical cover off. Matter of fact, I don't recommend doing it. Two prong outlets. Someone also asked about that. Make sure you call those out. You can put GFCIs where those are, but just know that uh, is acceptable in some areas. So the inspector shows safety tester. Make sure that if it is ungrounded, that you call every single one of those out. I try to check every single outlet I possibly can. The three wire appliances are now 4-wire appliances because it just became a safety problem or a safety issue, and so the prong dryer cord is more acceptable now than the three prong. So, and if you wanted to, you could read this video. Just go ahead and take a screenshot and watch that because he can actually do that. And I think receptacle blade patterns, I don't think we even need to discuss this. Have designed for 30 amp, cannot, yep. Standards of practice, check it out. Any InterNACHI.org/SOP. Really understand the standards of practice and follow it as best as you possibly can. I really hope you guys understand how GFCIs work. If you put one in, try to daisy chain them all the way down the line. And when you hit the one, it'll all go off, or you can get the one that goes in the circuit breaker. Where they are required is bathrooms, kitchens, garages, unfinished basements, laundry rooms, things like that are GFCIs. And hallways, living room, and stuff need to have GFCIs in bedrooms. So testing GFCIs, I think we all know how to test those. If you don't know how to test them, you can email me. So thank you for coming to class. I really hope you guys enjoyed this. I really enjoy doing these. Yeah, kind of ran out of time, but hey, that's a wrap.